I now call to order the Society's 2,346th meeting in the 144th year since its founding in 1871. Good evening, everyone. My name is Larry Elstein. I am the president of PSW, oldest scientific society of Washington, D.C., committed to providing a forum for further scientific understanding and inquiry. Welcome to our members and guests to tonight's lectures, celebrating the Hubble Space Telescope's 25th anniversary. Because tonight's program is longer than usual, I will forego the traditional reading of the minutes and the recounting of the 21st meeting of the Society 144 years ago. I will begin with some well-deserved thank yous, announce new members, introduce the program and our 6 speakers, and then turn the stage over to them. The lectures will be followed by a question and answer period with all 6 speakers. Thereafter, I will present the speakers with a small gift, make a few closing remarks, and adjourn the meeting to the social hour. Please join me in thanking NASA and the Space Telescope Science Institute for their help in putting this program together and for their support. I'd like to particularly thank individually Matt Mountain, who was instrumental in bringing this group of fantastic speakers together. Hussein Jurda of STSI, who has been wonderfully helpful in putting the program together. Jennifer Wiseman, who suggested the thematic approach of the program. And needless to say, our other speakers, Robert Smith, John Grunsfeld, Robert Williams, and Mark Clampin, for their many helpful suggestions, their flexibility, and their willingness to speak to us here tonight despite their impossible schedules. Please join me also in thanking the Policy Studies Organization in cooperation with the American Public University for sponsoring PSW's Fall 2014 and Spring 2015 lecture series. I am pleased to announce that Jennifer Armistead, a scientist at NIH, Michael Lavilla, a chemical patent examiner at the USPTO, tonight's speakers, Robert Smith, Robert Williams, Jennifer Wiseman, and Mark Clampin, have been elected to membership in the Society. You might wonder why John Grunsfeld and Matt Mountain are not on that list, and it's because they're already members of the Society. Please join me in welcoming them. This Friday is the 25th anniversary of Hubble's launch into space. The importance of the observations made by this singular observatory have been so profound that the telescope, many of the images it has gathered, are known throughout the world. It was not easy to fund Hubble, to build it, to launch it into the proper orbit. It was not easy to overcome its perfect optical flaw. It was not easy to carry out advanced space missions to fix it and upgrade this marvelous instrument so that today, 25 years after its launch, it is orders of magnitudes more sensitive and more versatile than when it was launched. Behind the many stupendous success stories, there is, I think, at least one theme running through Hubble's history, captured by one of our speakers tonight, Robert Smith, in his excellent book on getting Hubble built. From its beginning through to today, Hubble required, quote, speculative visions, brilliant insights, years of grinding work, triumphs and mistakes. Success has depended on human ingenuity and dogged determination, on the ground and in space, to create, fix, renew, and recreate Hubble, and to learn from it. We have the honor and the pleasure tonight of hosting 6 extraordinary speakers on Hubble. It would take all of our time to present just their major accomplishments, so I won't try. Instead, I will simply introduce them and let them celebrate 25 spectacular years for Hubble, for science, and for the world. Our first speaker tonight is Robert Smith. His talk, Getting to Orbit, will cover some of the pre-launch story of how Hubble was conceived and built. Bob is professor of history and classics at the University of Alberta, is a long-time close student of Hubble, and he is the author of the Space Telescope, a study of NASA, science, technology, and politics. Our second speaker is John Grunsfeld. His talk, Servicing Hubble, will focus on maintaining and upgrading Hubble, particularly on the manned Hubble servicing missions. John served on 3 servicing missions, including the final mission, which he championed after the Columbia disaster. He is fondly and respectfully known as the Hubble Hugger-in-Chief and the Chief Hubble Repairman. Currently, he is NASA Associate Administrator for the Science Directorate. Jennifer Wiseman, our third speaker, will give the first of 3 presentations on Hubble's contributions to science. Our talk, Planets, Stars, and Exoplanets, will focus on Hubble observations of our own solar system and the detection and study of planets around other stars. Jennifer is Senior Project Scientist, Hubble Space Telescope at NASA. Robert Williams will present the second talk on Hubble science, Deep Fields, focusing on Hubble's observations of some of the most distant, least visible aspects of the universe. Bob is Senior Research Astronomer at the Space Telescope Science Institute, and he served as STSI's director from 1993 to 1998. Mount Mountain will present the third talk on Hubble science, Cosmology, focusing on the way observations made with Hubble have profoundly altered our fundamental understanding of the universe. Matt is president of AURA, the Association of Universities for Research in Astronomy, and he served as director of the Space Telescope Science Institute from 2005 through 2015. In our final talk, Mark Clampin will present the final talk this evening, the James Webb Space Telescope and beyond, taking us beyond Hubble to the JWST, now under construction, and proposals for even more capable observatories to see beyond JWST's horizons. Mark is Senior Scientist, JWST, NASA. Following Mark's talk, there will be a 15 to 20-minute Q&A with all of the speakers on stage. So we'll hold questions until then. Please join me in welcoming our first speaker tonight, Robert Smith, to the podium.
So I feel like I've crashed a wedding anniversary. It's the 25th wedding anniversary. And everybody's very happy. It's been a triumph. But I'm here to say, remember, this nearly did not happen. It was very rocky at a number of points early in the relationship. And so I want to go back into what is now the very early history of Hubble and look at the period before the Hubble Space Telescope was launched and before the Hubble Space Telescope became the Hubble Space Telescope. I'm going to be talking about the large Space Telescope, and then when that was regarded by NASA as too opulent a name, it became the Space Telescope. So most of the time, unless I make a mistake, I won't be referring to Hubble, but that's why. Now, I was too optimistic. I thought I would get us to orbit, but in fact, I'm going to get the project approved. I won't even get it built, but I will at least get, in my 20 minutes, the project approved. So, I also thought, to kind of frame things, I would like to ask this question: why does Hubble matter? And I'm sure some of you will come up with other answers. For example, demonstration of the value of human spaceflight, for instance. And the remarkable scientific results and discoveries are going to be discussed by other speakers. I wanted to mention the issue of public engagement, because clearly I think it's clear that no other telescope has ever had the kind of impact that Hubble has had on public interest in astronomy. And the images of Hubble have moved through all sorts of different cultural spheres. They're on t-shirts, mugs, endless websites. And every year when I teach my history of astronomy class, I challenge my students to go through any decent-sized mall and not see a Hubble image somewhere or other. And I would invite you to try and do the same. But I think it also matters because it exemplifies what I think are key issues in the history of US science in the 20th century, and most particularly the ability to manage changes in scale. And if you were to ask me, well, what is the single most important thing about US science in the 20th century, that would be my answer: the ability to manage successfully changes in scale. And what I mean by that, I'll try and come back to at the end. I'll also talk about the influence of the Cold War. And I'll also talk about how Hubble helped to remake the American astronomical community in the mid-1970s during a 3-year battle from 1974 to 1977 to win political approval for the Hubble. And that's going to be my main focus. How was political approval won for the Hubble? And to actually win that political approval, the American astronomical community had to, in a way, remake itself, reinvent itself. And without that remaking, I doubt whether Hubble would have been approved, certainly in the form that it was and in the time period that it was. So let's go to a meeting in the White House to start. And these gentlemen, some of them may be familiar, I hope at least one is. But this is James T. Lynn, who was director of OMB in 1976. This is Glyford Stever, the President's Science Advisor, and that, of course, is President Ford. And at this meeting in 1976, they turned to discussing what was called by then the Space Telescope. And Stever told me later that normally in those kinds of meetings with the President, he would go in, he would explain, this is a really, really important scientific project. I know the budget is tight this year. Things are bad, but we really must support cutting-edge science and technology. But at this particular meeting, the President enthused about the telescope. The OMB director enthused about the telescope, and Stever told me that he decided he would just shut up and let them go. And the meeting was brought to a halt at various points as the President's Science Advisor, and the OMB director pondered what it meant to look back billions of years, look at galaxies whose light had travelled towards the Earth for billions of years. This was not apparently the normal sort of meeting with the OMB director, but these were already highly enthusiastic about the telescope. And so when Bob Williams starts talking about the deep fields, I think it's worth reflecting back to this meeting with the President, the OMB director, and the President's Science Advisor, because that, in a way, was fulfilling the aspirations that even leading politicians and leading policymakers had in 1976. But this Johnny Hart cartoon, which was part of that briefing, I think encapsulates the problem that the advocates of the Space Telescope had. And some of you probably can't read the legend, so let me do that. The secret, with the two cavemen are talking, the secrets of all creation, secrets that could mean the salvation of mankind are locked in those stars. Gosh, why can't we reach out and unlock those secrets? The key is not ours to have. How come? It ain't in the budget. And that was not a spontaneous outpouring of Johnny Hart. That was a planned, an advocate of the Space Telescope would call him up, says, we've got a problem. And this became a widely used cartoon in all sorts of different forums. And the problem was that by this point, certainly the White House was on side, but there was still considerable opposition in the Congress, and there had been a substantial opposition in the Congress since 1974 when the telescope first turned up for planning funds. For the White House, the key pluses about the Space Telescope were that it represented there'd been a national investment in the shuttle. So what was the point of building the shuttle unless there were worthwhile payloads to put aboard the shuttle? US leadership in science and technology, retaining American leadership in astronomy. There had been a slight decline that had started in 1969 in R&D funding, so here was a means to turn that around. And also the science was attractive. Witness contemplating what it meant to look back billions of years at the meeting between Steve, President Ford, and me. So the White House, as I say, was on side. This was the large part of it. This is obviously a very early concept of the space shuttle. John Grunsfeld didn't fly in this version of the shuttle. And there we have the large Space Telescope attached to the shuttle. So even from the early 70s, there was this linking of the shuttle and the large Space Telescope. So the White House was on side, the Congress was not. So to help frame the rest of the things I'm going to say, let me just very quickly give you a 1-minute version of the early history, the really early history of planning for a large space telescope. Well, the usual way of talking about the very earliest concepts comes down to pointing to a study in 1946 by the astronomer Lyman Spitzer, who will turn up again in this talk. He wrote a study for RAND looking at the possibilities of different sized telescopes in space, that is, telescopes with different sized main mirrors. Then in 1958, NASA was formed, so space astronomy took off literally and metaphorically. Before 1958, astronomers were essentially restricted to flying rockets and getting a few minutes of observation from above the Earth's atmosphere. After 1958, it was reasonable to start looking towards satellites, so you could get maybe years' worth of observations from above the Earth's atmosphere. So that was an enormous push. Then in the late 1960s, Spitzer and other like-minded astronomers were pressing hard for what was called then the Large Space Telescope. And the summary of their conclusions appeared in this. Scientific uses of the Large Space Telescope, it became known as Chairman Spitzer's Little Black Book, which is a reference to the Cultural Revolution in China, where Chairman Mao's Little Red Book was brandished at people. But at this point, things were still not moving very fast because it was a relatively small group of astronomers who were interested in building a large space telescope. And the basic message that kept coming from NASA managers was you need a solid community. You can't just do this with a tiny group of astronomers. But even so, serious planning was underway in the early 1970s, engaging lots of contractors, astronomers, as well as NASA centers, in particular the Goddard Space Flight Center and the Marshall Space Flight Center. And so that gets us to 1974, when we have, for example, this concept. There are other concepts, but the basic common element in all of these early concepts was a mirror that was 3 meters in diameter. This particular concept was going to have 7 scientific instruments associated with the telescope. It was going to be built by the United States alone. But then there was a period of 3 years from 1974 to 1977 in this effort to win support from the Congress that meant a repackaging, a revision of these plans, until we end up with what was approved. What was approved was a 2.4 meter space telescope. As I mentioned earlier, the name had changed from Large Space Telescope to Space Telescope. And there was also going to be an international partner now in the form of the European Space Agency. So it was not going to be a US alone effort, it was going to be a joint project with the Europeans. And so this political effort also went along with renegotiating what the telescope would be, what the scientific objectives even were. Now, the initial fight with the Congress was over priorities. And so planning funds were deleted from NASA's budget. In 1974, it might look like a piddly sum, 6.2 million, but remember, we haven't got the inflation in from the late 1970s, early 80s. But those planning funds were rejected because there's the argument, I won't read it out for you, but it was not a top priority project in what had been, for astronomers will be familiar with this term, decadal survey. There had been a decadal survey in 1972 where astronomers had got together, 23 lead astronomers, but then many committees and subcommittees had met to come up with a list. What are the key options for the astronomical community? What projects do we think are the really top priorities? And the Large Space Telescope had scraped in as a second level project. It was certainly not a top priority project. Here's a typical response, but we approved the VLA, and that was a top project. Another representative said, we are, quote, exploding with telescopes. And so the first order of business was to establish the priority of the Large Space Telescope. So those are the actual priorities of what was called the Greenstein Committee, because it was chaired by Jesse Greenstein. And so there's Spitzer, and there's Jesse Greenstein. And what we have is an older way of doing business here. We have basically a deal that's developed between Spitzer and Greenstein. And Greenstein gets all the members of his committee to write a letter saying, we would have supported the Large Space Telescope if only we knew about the progress that had been made more recently. Spitzer was on Greenstein's committee, so it was very easy for him to get involved, and they reach an agreement. And the basic agreement is Spitzer says we will talk about a balanced program. So astronomers who were ground-based astronomers, people who use telescopes on the ground, would not get so anxious about somebody coming to scoop their money away and use it for the Large Space Telescope. So all 23 members of the committee signed a letter saying, yea, verily, we support this. So the Large Space Telescope was never formally approved by a standard NASA committee. A standard decadal survey committee. So that was an older way of doing business, where elite astronomers work it out. But to get actual political approval, there would be a new way of doing business that was required to get the Space Telescope approved and to make it scientifically, technically, and politically feasible. There had to be a coalition that was formed, and that would in time involve astronomers, contractors, NASA, DoD, European Space Agency, friendly journalists, the White House and Congress. And this involved significant shaping also by NASA. I don't have time to get into the details of that. But it was the production of a coalition that was absolutely essential, I think, to winning political approval for the Large Space Telescope. And the two key figures for the astronomers were these ones. Simon Spitzer with the Space Telescope undergoing assembly. In the back of him, there he is photographed at the Lockheed Missiles and Space Company, and John McCall. But they were the leaders of a loose group of supporters. But there were hundreds. There were also other kinds of allies who were brought into the fight, even Superman, and his stirring story of Superman cleaning the mirror of the Large Space Telescope, employing his heat vision This again is not a spontaneous outpouring of DC comics. This was a plant by a contractor. So if I had the full legend at the bottom here, we would see assistance from Pete Simmons, Grumman Aerospace Corporation. Because Grumman was interested. Okay, this is absolutely standard. It's what George Ellery Hale did at the start of the 20th century. He would plant articles in the favourite journals of his patron. Advocacy, again we have a transition. This is Margaret Burbidge, who was president of the American Astronomical Society in 1976. She worked for Congress. She was not doing it formally because the American Astronomical Society were worried about their tax-exempt status, but it so happened she was an astronomer who happened to be the president of the American Astronomical Society. So, if it had not been for this kind of effort of advocacy, the telescope, I don't think, would have been approved. And so Hubble, I would argue, actually remade what it meant to be an astronomer. Astronomers had to realize that if they had priorities, they had to really get behind them. And it was not sufficient to stay in your lab or you're in your observatory. It meant much more direct kinds of engagement. Now again, a zero flashed at me, so let me be very quick. So the issue, I just wanted to mention the issue of cost. The initial issue with Congress was priority. Is this a top priority for astronomers or not? But then cost became the issue. And sometimes there was talk of a choke factor or a choke limit. Go above a certain cost and the Congress will choke on it. And that was very hard to deal with. But it's also worth bearing in mind that the cost of Hubble was clearly affected by its technical heritage. And it's in many ways, I think, a gift of the Cold War. That, I think, may be familiar to some of you. It's something that's been published more times, but it's central Moscow from a KH-4 or Corona satellite. Reconnaissance satellite that was first flown in the early 1960s. Here's George Keyworth, the President's Science Advisor, talking about Hubble in 1985. The Hubble is new, but it draws upon technologies used in military systems. If we look at the KH-9 hexagon reconnaissance satellite, the first one of these was flown in 1971. The main contractors were Lockheed and PerkinElmer. The main contractors for the Hubble Space Telescope were Lockheed and PerkinElmer. And so the earlier history of space astronomy was in many ways, in technical terms, pretty irrelevant to the history of Hubble. There was a break, and it comes with the introduction of this different technical heritage. So let me end by just saying that the management of scale that I mentioned at the start, I think, was absolutely crucial to the success of American science in the 20th century. One obvious example is Ernie Swaretz and the cyclotron, where we start with a 5-inch cyclotron, $1,000, one graduate student, 1930. 1939, construction's underway for a 184-inch cyclotron, $2 million, having gone through intermediate steps. George Ellery Hale is arguably the best example in terms of astronomy, and there's Hale with Andrew Carnegie and the great 100-inch telescope on Mount Wilson, which was funded by Carnegie money. And Hale, in his career, built 3 state-of-the-art observatories: Mount Wilson, Yerkes, and Mount Palomar, all involving changes of scale. And so, this is my main point. And why does this matter? Because sometimes people don't get it right, or the political forces are just too much. And so there are big costs to not being able to manage that scale. But with Hubble, the astronomers, in the end, NASA science managers, the contractors did get it right. They did win political support for the telescope. And here we are, and we're able to have this wonderful celebration of Hubble's results. But remembering the very rocky start, indeed. And it was not ever a done deal. And there were moments when it could well have been cancelled. So with that, let me end, and I'm sorry I went over.
All right, so with that, of course, there's so many wonderful lessons there, including the fact that Hubble, even after making it to orbit, was canceled. And so let me start with a couple of questions, and you're probably wondering why I'm showing this. But first of all, who saw my talk about a month ago? Okay, good. There's not unanimous. Okay, second is, I want you all to look around at each other this time. Who in the audience, and I'll raise my hand too, who has actually worked at one point or other during their career or been associated with the Hubble Space Telescope? So look around, there's a lot of hands. It really is just a remarkable effort that started with Lyman Spitzer and others and has involved the most amazing team, the most amazing community towards a very lofty goal. And as the reason for existence of the Hubble Space Telescope was widely appreciated, in the case of the superconducting super collider, the high energy physics community, at least I felt, and I came from the astronomy side, so it's easy to give you my perspective, that they felt a sense of entitlement and were not articulating the reasons for why they really needed this large collider, other than to, quote, smash atoms together and see what happens. And I think the fact that the Hubble Space Telescope was designed to answer these fundamental questions about where did we come from, where are we going, and not so much are we alone, but that's what we're asking now, addressed our fundamental human nature in a way that was able to get it over that hump several times. Now, why am I showing this picture? Because we talked about the history of telescopes a little bit. We talked about Hale and his remarkable achievements going from a 4-foot Yerkes telescope to a 200-inch Palomar telescope. And it's about the power of optics. And we all start in the power of optics with our human eyeballs. We know what that produces. Amazingly, nature has provided us with incredibly high-definition optics, our eyes. And for the history of astronomy up to Hubble, we got amazing views of the universe, of many fuzzy objects, that vaguely looked like something interesting that astronomers had to convince us were actually interesting. But Hubble, for the first time, was able to show us the beauty and grandeur of the universe with the kind of definition that our eyeballs see our normal daily life in high definition, color, and depth, bringing it to life, and even now through computers, to 3D. So this is a picture that I took on the last servicing mission of Drew Feustel, showing a ball of water, which of course is a lens. And we know that lenses can modify light. And we'll hear about gravitational lenses perhaps a little bit later. But this is a simple optical lens, convex lens that inverts the image and magnifies it. His nose really isn't that big. And of course, if you put your eye up to an eyepiece of a telescope, it allows you to increase the power of your eye many-fold. And so Drew sees an expanded image of me taking a picture of him. And so, of course, that's what Galileo did with his small telescope, a very crude telescope, but provided about 70 times more light gathering power than the human eyeball. This is an almost identical, well, it's not as identical a telescope as we can get today. It's a replica of Galileo's telescopes with the same glass, the same leather, the same wood from the same forest, same period techniques of polishing. And it was a really lousy telescope, especially compared to the Hubble Space Telescope behind it, by any measure. In fact, at best, a teenager would say this is a piece of junk compared to what I had as a little Sears 70mm telescope as a 12-year-old. And so it is this power of the telescope that's part of our story, going from Galileo and the privately funded race to build bigger and bigger telescopes, but then the invention of photography. And then we were able to take time-lapse, time exposures, increasing the sensitivity, and finally bringing these images into light. And then the electronic detectors. But it was Hubble being above the atmosphere, being steady, and you'll hear more about this in the other talks, especially the deep fields, that we took a quantum leap in the ability to improve over the human eyeball. And most recently, with this last servicing mission, to take another leap, with newer detectors taking advantage of technology, providing what amounts to 100 billion times more capability than the human eyeball. Really phenomenal. And this is what's allowed Hubble to bring the universe to us, or to allow us to time travel back to the beginning of the universe. As you heard from Robert, the path to Hubble was very rocky, essentially synchronous with the start of NASA and the start of the Space Shuttle program. 2 weeks ago, we celebrated the first flight of the Space Shuttle, 1981. Really remarkable. Hubble was built in 1985. We lost Challenger in 1985. Hubble almost didn't happen for that reason. But Hubble was co-designed with the Space Shuttle to fit with the shuttle. The shuttle was co-designed to be able to service Hubble so that we could put in those new scientific instruments and take advantage of it. Now, full disclosure, the original idea was that we would bring Hubble back, refurbish it on the ground, and relaunch it when we needed to do that. I'm convinced that if we ever brought it back to the ground, that would have been the end of Hubble. But in 1990, a crew did launch the Space Telescope, renamed the Hubble Space Telescope on Space Shuttle Discovery. You see it out of Hazy now, which is another way of saying we can't go back to the Hubble, the shuttle. And the results were spectacular. Just what was intended. Hubble was part of the Great Observatory program. It started Hubble, the X-ray Observatory, Chandra, the Compton Observatory, and the gamma rays, and Spitzer, and the infrared. And Hubble was indeed kind of a good telescope, maybe. In fact, it was a huge disaster for NASA. The spherical aberration, the mirror was ground to a perfect shape, just the wrong shape. The best optics we'd ever created for a telescope or any optics in space, and again, just slightly, much less than the width of the human hair, the wrong shape. And this is one of those mini comics, much as the ones that supported Hubble early on. There's a whole book of these, of things criticizing Mr. Magoo's telescope, picture of the moon, of Jupiter, Saturn, and of most important, angry taxpayers who had spent all of these precious funds to build the Space Telescope. But again, the team was incredible to come up with a fix. And we were able in 1993 to go back, put in the corrective optics. It's a story hopefully you all know. As Senator Mikulski says, the contact lenses on the Hubble, they're actually mirrors. It's irrelevant what they are. They corrected the vision. But more importantly, this was part of the story of the Hubble Space Telescope. This was a story about women and men in white suits riding to the rescue, not only of the Hubble Space Telescope, not only of the future of astronomy, but of NASA. Because if NASA couldn't launch and then subsequently repair a telescope with such a simple problem, how could it ever build a space station? How could it ever keep flying the space shuttle? Why should it fly the space shuttle? And if we shouldn't do the space station, keep in mind that's 1990 to 1993, well, if we shouldn't do the space station, then we have funds that are freed up to do the superconducting super collider. And of course, that was the political agenda at the time, pitting particle physics against astrophysics. It's always a good strategy for all the scientists to circle the wagons and shoot inwards. Hubble prevailed, the space station prevailed, and of course we're thankful for Hubble, and we ceded high energy physics to Europe. That's the quick story. But in space astronomy, we're still leading the nation and the world with the Hubble Space Telescope, a partnership with ESA. In 1997, we took advantage of new advancements in detectors and put in new instruments. And then in 1999, Hubble ran out of gyros and stopped doing science. We mounted a rescue mission, put in new gyros, a new fine guidance sensor. And then in 2002, and that was my first mission to Hubble, 2002, we put in the advanced camera for surveys. Keep in mind, when Hubble was launched, there were no digital cameras in the world. It hadn't been invented yet. Even the CCD was still in its infancy and hadn't been used for anything practical, at least in the unclassified world. And it was very crude. Even Wide Field Planetary Camera 2 had a very crude digital camera. But with the advanced camera for surveys, finally we were launching something into space that was still years away from making it into Walmart. A super duper digital camera. And it is still a state-of-the-art digital astronomical instrument on orbit today. We repaired the near-infrared camera. did another rescue of Hubble with the power system, and finally, in 2009, just 6 years ago, we did a complete makeover of the Hubble, took out those corrective objects, put in a new wide field camera with incredible capability. You'll see the results of that in some of the next talks, and really set up Hubble for hopefully a very long lifetime. Now, it says deorbit mission up there because at some point Hubble is going to come back into the atmosphere. But fortunately, mystery of science. Is that the Hubble, right? No, another great mystery of science is that the sun has been incredibly quiet. And that's been very lucky for us with Hubble because the atmosphere hasn't swelled up because all this solar radiation is flowing into the atmosphere. So Hubble is going to make it to the 2030s. Pretty remarkable. So I'm not worrying about a deorbit mission. I just want to show you a little bit of what it's like to do a servicing mission. This is the crew. Scott Altman was our commander. He was a repeat flyer from the 2002 mission. I wanted someone who had experience. Mike Massimino, spacewalker from the 2002 mission. So that was the cornerstone of our experience. Scott was on his 4th mission, Mike Massimino on his 2nd. I was on my 5th mission, my 3rd to the Hubble. My spacewalking partner, Drew Feustel, an exploration geologist, Megan MacArthur, an oceanographer, our flight engineer and robotic arm operator, Greg Johnson, our pilot and a naval aviator, and Mike Good, Mike Massimino's spacewalking partner, an aerospace engineer from the United States Air Force. Now, Hubble had been canceled. In 2004, Sean O'Keefe, the administrator of NASA, had canceled future Hubble missions on the basis of risk. Risk to the agency, risk to astronauts, risk to the space shuttle program. Mike Griffin put it back, assigned us to go fix the Hubble. But to do so, we had 2 space shuttles. Atlantis, which was our ride, and Endeavour, which was a rescue vehicle in case we needed it. So we had to make sure we turned left at the junction to get to Atlantis. You can see the name there. Scott Altman's confirming that. We have our orange suits on, our parachutes. That's to make us feel better. We're not going to jump out of the space shuttle. It takes about 10,000 people to get the space shuttle ready to go. This really is an all-NASA effort. People at Johnson Space Center, Goddard Space Flight Center, Maryland, Florida, Huntsville, Alabama, and many of the contractors are the lowest bidders. Something to think about when you're on your space vehicle. 6 seconds before launch, the main engines start up. Then the solid rocket motors go off. If you ask me later, I can tell you about that master alarm. That's a bad thing. Off we go to the Hubble. But because of that master alarm, we're wondering if we're going to get there. But we did continue at 2 minutes. Those solid rocket motors run out of fuel. Dumped those. They spun around and landed in the Atlantic Ocean. They were picked up and will be reused. The camera also watches us sail off with our hydrogen oxygen main engines. 8.5 minutes later, we're doing 17,500 miles an hour, orbiting the Earth, trying to catch the Hubble Space Telescope. We dump that big orange tank, that's our liquid hydrogen oxygen tank. That'll burn up in the atmosphere over the Indian Ocean. We open the payload bay doors, and even though we got shaken incredibly inside of the cabin, strapped to the vehicle, all of the stuff in the back of the space shuttle were on springs, on soft ride. They made it just fine, which is fine with me as an astronomer. I wouldn't want to open the payload bay door and have little parts floating around. That would be bad. So we made it to orbit. Scott Altman then started flying the space shuttle to get underneath the Hubble. This was actually the 3rd day on orbit. This is Megan MacArthur's 3rd day on orbit, her first space flight, and the first time she's ever flown the robotic arm. Because all she's ever done before is play a computer game with the robotic arm driving an imaginary helmet. So here she is reaching out to grab the most significant scientific instrument ever created by humans, an international resource, and she has one chance to grab it, probably worth about $16 billion at this time. A lot of focus there. And fortunately, she did a wonderful job grabbing it because had she not, I'd be in Bolivia in exile. I don't know where she would be. We agreed not to tell each other just in case. But she grabbed the Hubble because you only get one chance and put it into the payload bay, which allowed me to go out for a walk. Wow. And this is what I really love doing. I like giving talks at the Cosmos Club. Don't get me wrong. But I'm truly happy in my place out spacewalking. You can see the Earth reflected in my visor. I have a big grin. That grin was short-lived, however, because we couldn't get the old camera out. And we tried, and there was a stuck bolt. Everybody was really worried. You can see Megan looking worried. But fortunately, we have lots of help. We were able to call the ground. There was some Pappas brothers, go ahead, Florida collar, no problem. And fortunately, we were able to get that bolt unstuck. We were able to replace gyros, we were able to replace batteries, replace scientific instruments, all in these bulky spacesuits. We even opened up the inside of the instruments, the advanced camera for surveys and the Space Telescope imaging spectrograph, taking out hundreds of tiny screws, not losing a single one, to be able to replace circuit boards inside the telescope. Occasionally we ran into problems. Mike Massimino stripped a bolt and we couldn't get a handrail off. And again, the ground was there to help us. And they said, hey, you know, maybe you can get that thing off by some means. And here he goes. Let's rip it off is what they said. Now, how would we know we could do that? Well, fortunately, while we were doing the spacewalk, it took 4 hours to get to that point, the folks on the ground put together a mock-up and tested it to see if it would work. And you saw it going flying there. And the best news is they didn't show us that video. Dave Lacombe was probably going out of his mind on the ground, but you know, maybe they showed him. They didn't show it to us. And it's a good thing, because had they shown it to anyone at NASA, we never would have done it. No, it's unsafe. So finally, we were able to put in another fine guidance sensor, one of the instruments that will hopefully give Hubble a very long life, and is one of the keys. It's an interferometer that allows it to point very steadily. Megan was able to grab the telescope again, lift it out of the payload bay, and off Hubble goes. Now, there's always a question at this point. Did we fix the Hubble or did we break the Hubble? After all, it's a sensitive telescope. It's not a space station you can kick and things like that. And we'll have to save that for the other speakers. But of course, you know that we did fix the telescope and it worked great. And so we were able then to, as Hubble disappeared, look out the window a little bit, watch a sunrise. This happens to be a sunrise. And I just want to reflect on this picture a little bit before I hand it to the next speaker. That, you know, we live on a really beautiful Earth. And when Hubble was launched, we knew about the Earth, we knew about the 9 planets in our solar system, subsequently demoted to 8. July 14th, we're going to the dwarf planet Pluto with New Horizons, so pay attention to that, of course you will. And looking out at planet Earth, it's really striking how thin our atmosphere is. And one of the things that Hubble has done, and Jennifer will talk about it, but Hubble was able to do spectroscopy, to analyze the components of the atmosphere of a planet around a nearby star. And when she talks about that, it's going to be really phenomenal, because when Hubble was launched, we didn't know about any exoplanets, just the planets in our own solar system. And the light that we're analyzing with Hubble has to go through a similarly thin atmosphere and make it all the way to us across the galaxy. So with that, I will hand it over to Jennifer to prove to you that we didn't break the Hubble. Thank you.
Okay. I don't suppose dimming the lights a little is possible, or does that disturb the video? Well, we'll go with this, but some of these images are very nice when the room is dark. I want to talk to you about some of the things we're learning with Hubble and some of the wonderful imagery that Hubble has enabled us to receive, as well as some detailed scientific data that we're getting because of the telescope. So there is Hubble, and I can't tell you how grateful we in the scientific community are to the astronauts and the 10,000 people that John mentioned to help the shuttle program be successful, and all the people around the world who've worked on this mission to make it successful. Because right now we're saying, and it's absolutely true, that Hubble, even after 25 years, is at the peak of its scientific return right now. It's very powerful. We have a whole suite of operating scientific instruments on the observatory. It's doing a fabulous job, and the little cliche that we use, which is absolutely true, is that Hubble has changed the textbooks. It's given us information that has really revolutionized our understanding of the universe and our place in it. Here's an example of a fabulous image. This is the Omega Centauri star cluster. This image was actually first taken in a way to calibrate the newest camera put on Hubble, thanks to John Grunsfeld and his team. And it's so spectacular that we use it now for many of our public talks, because it shows you a lot of things. It shows you the beauty of stars. This is a dense star cluster in our galaxy. It also shows you something about the precision of Hubble, the high angular resolution that we can get by being above the atmosphere with the telescope. And on a night like tonight, I think you can understand the value of having a telescope that's above the clouds. First of all, we don't have to worry about weather, and second of all, we don't have to worry about the atmosphere at all. That can blur the images and the data coming down to the telescope. And the atmosphere even blocks some wavelengths of light entirely from getting to the ground. So putting a telescope above the clouds is very advantageous, and we can see things like this. It's helpful to see in context where a dense cluster of stars like this would exist. So this is an image taken not with Hubble, but with a telescope on the ground that gives you a much broader field of view toward the galactic center, where you see a lot of dust and material and a lot of stars and larger blue objects here that are actually clusters of stars. And we're going to zoom in from this wide field image to the image that Hubble can see. So you can see the context of that cluster. Here's the constellation in this area. As we move into the Centaurus area in the constellation, we move into this one, what looked like a star, but now we see it's actually a cluster. And we continue to zoom in and transition over to that Hubble image, where we don't get the broad field of view, but we do get this high angular resolution that allows us to differentiate star from star, even in a crowded field. This is really important not only for the beauty of seeing how star differs from star in color and brightness, but also scientifically to differentiate star from star in terms of temperature, composition. If you can separate star from star, you can do detailed analysis of how these clusters form, how the stars form, something about the history of how the stars got there in the first place. So this is a huge scientific leap that Hubble will enable for us. I also think, given that we're here at the Philosophical Society of Washington, and I thank you for the warm welcome you're offering me here, that I should offer you a philosophical quote. So Immanuel Kant, philosopher, said, and I paraphrase, something like this: two things continue to fill my mind with ever-increasing awe and admiration the more my mind dwells upon them. Those two things are the starry heavens above me and the moral law within me. So there's a great quote for you to think about tonight on your way home. All right, so I think it's helpful just to remind ourselves of a little context. This is an artist's conception of our own galaxy, the Milky Way. And our solar system, our sun, would be out here about 2/3 of the way out from the core. We can't take a picture of our Milky Way because we don't yet have the capability of sending something far enough out to take a picture and send it back. But we can get a pretty good idea by looking around from where we are. We know there's a bright galactic center and bulge of stars. We know there are these spiral arms. And most of what we look at with Hubble would be within a few thousand parsecs of our solar system, at least some of the iconic images that you're used to seeing. But that's not all Hubble can do, and you're going to hear a lot more about that in these subsequent talks. But let me mention this. While that cluster of stars I just showed you is in our own galaxy, Hubble's sharp resolution can even differentiate star from star in other galaxies, some of the nearby galaxies in particular. This is part of Andromeda Galaxy, which is 2 million light years away from the Milky Way, and yet Hubble is capable of differentiating star from star. This is only part of Andromeda, because Andromeda fills a huge field of view, and so we have to image it by mosaicing many different pointings from Hubble. This is something, a product of something called the Panchromatic Hubble Andromeda Treasury Program, or FAT. That is something that has been undertaken by a large group of astronomers over the past few years, and it truly is spectacular what we can see, even in another galaxy, when we can differentiate star from star. All right, colorful nebulae. These are some of the most beloved pictures that Hubble has provided for us and for the public. They are beautiful, but they also signify to astronomers activity, and in particular, they signal the birth and ongoing birth of new stars, and presumably the planets that we now believe are around many, if not most, stars. So here are some of these beautiful images. This is a portion of something called the Monkey Head Nebula that was released a year ago in celebration of Hubble's 24th anniversary. In many of these nebulae, you see these features, which would be a dark region that you can't really see into because there's so much dust obscuring the view and the density of this interstellar material. Then you often see these bright lit up columns around the edges. There are bright stars that have recently formed outside the edge of these nebulae, and their stellar winds and radiation can rain back onto the surrounding material out of which they formed and carve out columns and cavities and create just a spectacular visage of the birth area of stars. Here's another spectacular region. This one are pillars in the Carina Nebula. Again, you see this phenomenon of dark pillars of dust. Let me see if we have a little video here that can give you a sense of a 3D, Mystic Mountain. Doesn't that sound compelling? As we look close at this nebulous region, we do see, again, this combination of light from young stars that have recently formed, raining down, blowing away, the radiation and winds are blowing away the less dense gas, leaving behind for longer the denser gas. And it's in that denser gas that new stars can continue to form. And you see these odd features here that look like jets. Well, in fact, they are jets. It turns out that young stars, as they form, go through a stage of expelling material due to the magnetic fields around their core. Material is falling in. Some of it gets caught up in magnetic fields, gets expelled as jets. When astronomers see these expelling jets, they know that buried down in the middle here must be a star in formation. We call that a protostar. So these are truly ongoing active sites of star formation. We also see features like that in this very famous iconic image, the Eagle Nebula, which came out in 1995. This is the most famous image Hubble has ever taken. We redid the image last year with the new camera that John Grunsfeld and his team installed on Hubble, the Wide-Field Camera 3, developed largely at Goddard Space Flight Center. And with the new camera, we get a larger field of view, we get more detail in the image, and you can again see a region where massive stars have formed, and they're chiseling out these regions where the denser material is remaining behind. The difference is that the Wide-Field Camera 3 also has an infrared channel, so we can see inside these dense columns in infrared. And now we can actually see more stars because infrared can see through some of that dust that would be obscuring the light from some of these stars. And we can even see hot spots within these columns where new, what we call protostars, are coalescing and getting hot and starting to form. So Hubble gives us the ability to see where our eyes would otherwise not be able to see. These columns have sometimes been humbly referred to as the pillars of creation. All right, here's another just beautiful ethereal image of one of these interstellar clouds, the Horsehead Nebula, but using the infrared channel on the Wide-Field Camera 3, we see much more of the kind of wispy material surrounding the Horsehead Nebula, and it's just a beautiful, beautiful feature in space. All right, by the way, if you like these images, you can find them all on hubblesite.org. We have a whole gallery of images, and also we have a website for the 25th anniversary, hubble25th.org. Let's look down in this region. A lot of you will recognize this as Orion. This is a ground-based telescope image that gives you a large field of view, but if we zoom down into this region down below, you see a nebulous area, and it turns out, zooming in with Hubble, you see this type of beautiful feature Again, colorful gas. The colorful gas is colorful because newly formed massive stars actually have enough radiation to ionize the surrounding gas, and it gives us this beautiful visible color. It tells astronomers that star formation is continuing in this region, and if we look a little bit closer down in here, we also see something very interesting. So here is the inner region of there, some of these bright stars that recently formed. But if you look very closely, as astronomers did, you also see some smaller objects here and there. These are bright little objects that are enshrouded in these dark disks, these silhouetting disks that appear to be dusty donuts, basically, dusty disks around bright objects. And it turns out these are young stars are trying to form. They're surrounded by dusty disks. The diameter of these disks is about the same diameter as our solar system. And so it gives us a sense that maybe stars and their planetary systems form in this way, that stars form with dusty disks and that planets may form in these regions around stars. And in fact, now studying these disks of debris around young forming stars is a very hot topic in astronomy. It turns out that stars seem to all or mostly go through this phase as they form of having a lot of material in a disk around them. And it's in these regions where we believe planets form. And not only that, we've actually found some planets in these regions. Here's a star much closer to us than Orion, that Fomalhaut star system. With Hubble, we looked at Fomalhaut, blocked out the central star, which is very bright, so that we could see the material around it. And it revealed not only this dusty ring, which signals maybe something's carving out that ring, maybe a planet, but actually we spotted the object which we now think is a planet orbiting Fomalhaut. You can see over the years this object has been seen repeatedly with Hubble. So Hubble has actually directly imaged a few planets like this one outside our solar system. Let's talk a minute about our own solar system. Hubble is revealing a very dynamic solar system of our own. Let's think about our favorite planets. One of them is Jupiter. Jupiter is just spectacular, as seen with Hubble, with these fabulous bands in its atmosphere. And of course, the famous great red spot that we've all learned about as being a giant storm. But surprisingly, over the years, Hubble has noticed that this storm is actually shrinking. It's changing in size. The weather on Jupiter is changing. Now, what's interesting is that we might not have ever noticed that had we not have had Hubble all these years. So one of the advantages of having Hubble 25 years is that we can watch things over time and see how they change and evolve. We see things like comets. This is Comet Ison. Hubble has even spied colliding asteroids and disintegrating comets in our solar system. Things are not always calm and peaceful. Here's asteroid T2013 R3 that appears to be disintegrating. Here's another asteroid which actually appears to be the result of a collision of asteroids going on. That creates dust that fills our solar system. Here's a comet actually disintegrating before our eyes, Comet Schwarzman-Walkman 3, which I can't say very well. And then a very famous comet destruction in 1994, right after the repair of Hubble, when Comet Shoemaker-Levy 9 actually started becoming tidally disrupted as it was being drawn in and falling into Jupiter. This was a very exciting time. We have some astronomers here who are right in the middle of that, including Heidi Gamble sitting there somewhere. Where is she? There she is, right here. All right. So all these fragments were labeled. I believe there were 20-something fragments, is that right? That were eventually identified. These are the astronomers at the Space Telescope Science Institute poised for all these fragments to plunge into Jupiter. It wasn't really clear what would be seen. And in fact, this was what was seen. The material fell in, object at a time, sometimes on the back side, but then as Jupiter rotated, you could see the leftover impact sites and even debris, as I understand it. I was trying to understand today at a science conference what debris there would be in a gas atmosphere, but I was assured that you get particulate material that actually creates debris. It's quite interesting, but it's also a little scary because this is the size if it had impacted Earth. These are the size of those impact sites. So the solar system is not an entirely safe place to be. And then, lo and behold, this was only supposed to happen every 100 years or so, but then just about 15 years later, we had another impact on Jupiter right after this final servicing mission that John Grunsfeld told us about. And we weren't even really ready to start using the new cameras and things, but people got going and pointed the telescope and were able to see another impact, this time without all the large debris fields. So we think that may have been an asteroid rather than a comet that impacted Jupiter in 2001. So another thing we want to point out is that Hubble has the ability to see in wavelengths of light that are not visible to us, including ultraviolet light. And that's particularly important for seeing what we call the unseeable ultraviolet emissions from planets. We can see aurorae, such as here on Saturn, here on Uranus. Important to note that these change, these aurorae, and even where they are, changes over time. Aurorae of Jupiter. Jupiter has a strong magnetic field that also impacts its large moon Ganymede, and Ganymede also has its own magnetic field, and the interactions of these magnetic fields actually create changing magnetic field environments on Ganymede. We just announced that this year, a very interesting result, where a scientist realized that if there was a saltwater ocean under the ice in Ganymede, it would actually generate a kind of counter-current or counter-magnetic field that would affect the global magnetic field environment in Ganymede, and it would actually affect the positions of these auroral ovals. So here's an image taken from Galileo, a probe of Ganymede, and then the blue emission here is from the Hubble Space Telescope's ultraviolet capabilities showing the aurorae. We expect the aurorae to rock back and forth a bit as the magnetic field environment changes around Ganymede, but that rocking will be suppressed if there is an underground saltwater ocean. And in fact, the rocking motion is suppressed by quite a lot. So now we believe, because of this, that we can tell, just by these remote observations, indirectly, that there's an under ice ocean on Ganymede. Very clever. There might even be an ocean under the ice on Europa. Again, this compilation image taken from probes that have gone to the Jupiter system, but we can see with Hubble evidence of the components of water or water vapor being exuded from perhaps the cracks in Europa, and giving us a way of studying water under the ice without necessarily having to drill under there. So we're waiting for confirmation of this. This is an artist's conception of what might be going on there. Very exciting ways of using Hubble to determine indirectly what might be going on these moons and planets in our solar system. We're even discovering things we hadn't seen before, including previously undiscovered moons around Pluto. This is interesting in its own right, but it's also helpful as we are preparing for the NASA New Horizons mission to arrive at Pluto this summer, and charting a course that may be able to avoid most of the debris around Pluto is very important for the success of that mission. And that's a contribution that Hubble has made. And even looking beyond Pluto, what can New Horizons do beyond that? Well, I don't know, but we can at least tell here's an object here that's been seen by Hubble beyond Pluto that's only 34 miles across. So there's a lot of stuff out there. All right, I'm getting the zero sign, so let me just say a couple of things about exoplanets. Hubble has not observed Earth because we don't use Hubble to look down. But we do think a lot about whether or not there could be other Earths out there. And we wonder if there are planets outside our solar system. The last few years, there's been an explosion of discoveries of planets outside our solar system. We call them exoplanets. Many of those discoveries have been made with other telescopes, like the Kepler telescope here, which was a NASA telescope responsible for discovering many exoplanets. Also, telescopes on the ground have done a fabulous job. Here's a real system, an artist's conception of a real system discovered by Kepler of another star with planets orbiting around. The discovery rate over the years has just skyrocketed. So starting from the late 1980s and early 1990s, when we knew about hardly any exoplanets, over the years, the discovery rate has increased unbelievably. Hubble doesn't make those discoveries, but what Hubble does do is analyze exoplanet atmospheres in a very unique and pioneering way. So this is an example of an exoplanet, an artist's conception of an exoplanet that Hubble has studied. How does Hubble do it? Well, Hubble looks at the background, or the star that the planet is orbiting, and as the starlight passes through the planet's atmosphere on its way to our telescope, we can study something about the atmosphere. So here's what we're talking about. We have a planet orbiting a star. The starlight will be blocked by the planet for the most part if it's orbiting along our line of sight, but some of that starlight will pass through the surrounding atmosphere and then end up at our telescope and be received by one of our spectrographic instruments on Hubble. A spectrograph can spread out the light into its constituent colors or wavelengths. If some of those wavelengths have been absorbed by atoms or molecules in the planet's atmosphere, it will leave a big dark spot in that particular color or wavelength band. So you can look at the spectrum and see what's absorbed, and a spectroscopist can then infer what the composition of that exoplanet atmosphere must be. So Hubble was the first telescope to actually detect sodium and several other atomic components of an exoplanet, in this case HD 209458b, sodium, hydrogen, oxygen, carbon, and then later on the detection of methane, and more recently even water vapor in several exoplanet atmospheres. Hubble is still mostly looking at large exoplanets, gas giants, things we call hot Jupiters, and some super-Earths and Neptunes. But we're working toward the time of being able to use telescopes and future detectors to study planets more like Earth and to study the compositions of their atmospheres, and even someday to be able to detect if there's signs of life. All right, so that was a very quick tour of stars, planets, and exoplanets. All of the things I talked to you about, mostly the images and things, are in our galaxy, which we think looks something like this. This is another galaxy, which is beautiful, that Hubble has imaged, or in nearby galaxies. But we now know that there are a whole lot of other galaxies. In fact, hundreds of billions of them. And so I'm going to hand this over now to Bob Williams, who's going to start telling you something about how Hubble is able to tell us about many, many, many of those hundreds of billions of galaxies. So thank you very much.
It's a pleasure to be here addressing you on your 2,346th meeting. I can't speak to what's happened in the previous 2,345 meetings, but I think you'll agree that what we are talking about tonight is something that is significant. And thank you for election to this society, who's governing you as a member. So the topic tonight is Hubble Space Telescope and the science of astronomy. What is astronomy about? It's about everything that's out there, and we're trying to understand it and what makes it tick. And there are several themes that guide us in this study, and one of the principal themes is that the universe is expanding. That was a fact that was pointed out by Edwin Hubble. Very important, because the fact that the universe is expanding indicates that there is constant change, there is constant evolution. There's a beginning, because if you extrapolate backward, the universe was in a very hot, dense phase. So there was a beginning, and we know that the physical parameters that govern natural laws, that are not governed, but are subjected to the natural laws, they change. And so we want to try to piece together this story of evolution. And in order to arrive at what's happening out there in the present, we need to study the past, because it's always the past that has brought you to the present. And astronomy is the one discipline that enables you to see directly into the past. And that is because of the light travel time. You see the sun as it actually was 8 minutes ago. You see the nearest stars as they were years ago. The nearest galaxies as they were 1 million years ago. And so the fact is, we can piece together the evolution of the universe by looking back in time. Obviously, the further away you look, the further back in time you see. And since when we extrapolate back our current expansion in the universe, to know that the initial phase was about 13 billion years ago, the fact is, if we see back that far, we can actually determine what the physical state of objects in the universe was. So as great as archaeology and paleontology are that study artifacts, right, you got to piece together the past. We actually see. And Hubble Space Telescope is just a great facility that enables us to do that for two reasons. It's above the atmosphere, and therefore you don't have the background that the atmosphere provides. And so if you're going to look for distant objects, which are faint, you need to have as low a background as possible. And the Earth's atmosphere, even from your highest mountaintops, of course, does give you an appreciable background. In addition to, of course, the atmosphere disturbs the light, and so Hubble being above that gives you very sharp images. So the fact is, if we are to study the evolution of the universe, Hubble's the instrument to do it with, and therefore, taking long exposures of whatever is out there was a necessity for Hubble Space Telescope, an absolute no-brainer. It had to be done. Nevertheless, there were people who, within the community, thought that it was not a good idea, and some of them were rather significant people. In fact, the two primary advocates of Hubble Space Telescope, Lyman Spitzer and John McCall, as you can see in this article, which was published in Science magazine the very month that the telescope was launched, April 1990, one of the conclusions that John McCall and his colleagues at Princeton at that time came to was the fact that we do not expect HST, Hubble Space Telescope, to reveal a new population of galaxies. In agreement with previous authors, their analysis, which actually was quite detailed, suggests that the major contribution for galaxy research would be revealing shape sizes of previously unresolved, that is, previously known galaxies. So they really thought that, although in principle it was a good idea to try this, that in fact we'd come up empty-handed. And the reason is, the further out you go, the fainter things get. And their analyses indicated that the most distant galaxies would basically have sufficiently low surface brightness, that is, low intensity, that even with Hubble you wouldn't see them. And so this no-brainer basically was something that was very difficult to convince the scientific community. Fortunately, at Space Telescope Science Institute, we had some very bright young people, and one of them was my colleague, Mark Dickinson, who actually was a postdoc at that time, didn't have a permanent position, and he was interested in moderately distant galaxies. This one, that was in a cluster of galaxies, that's a third Cambridge catalog, source 324, that is at a distance of 7 billion light years, and recall that's about 50% of the way back to the Big Bang, which was a great distance to see a galaxy at that time at optical wavelengths. He was successful in getting, at that time, which was 1993 and 4, the Telescope Allocation Committee to approve a 32-orbit program. Hubble makes 16 orbits each day, so this was 2 days with that telescope, which at that time was a huge amount of time. Realized that after spherical aberration, was corrected, tremendous interest of the community to get time with the telescope. And so taking it for 2 days was really something. In any event, this image that Mark obtained of these distant clusters of galaxies was a game changer. And we continually talked about it. When I remember at Science Coffee, he brought up and showed this image. Because some of us had thought it was a really important idea to take a deep, long exposure, in spite of the prevailing sentiment in the community that, particularly after spherical aberration, which was a costly correction, right? Each launch is of the order of $1 billion, and the cost of Hubble at that time was in excess of $2 billion. So here we had a telescope that was referred to by my son, who now works for Microsoft, who said, "Dad, how's Hubble Space Telescope?" So it hurt the joke. You saw the political cartoon that John showed. Of course, it was on the Tonight Show with Johnny Carson all the time. So there was a feeling that if someone tried an observation that was more extensive than this and came up with a negative result, that would make public news, and it would be very bad for the telescope, which already was not a favorite of the American taxpayer. In any event, this game changer was that this galaxy, here and you can see some others, okay, here's a blow-up. They do not look like any of those nice galaxies that Jennifer just showed you with an isometrical shape. And so instantly, some of us said, gotta do it. Gotta take a very deep exposure. And so we did that. As director of the Institute, I had up to 10% of the time on the telescope. And so, in spite of what other people may think about it, there were a group of us at the Institute who, with the advice of an advisory committee, formed this program basically to take the deepest exposure that we could of one area of the sky to the point where you started getting decreasing returns on it. And according to our calculations, that would be a 150 orbit program, which is basically 10 consecutive days with the telescope. And we called it, we basically implemented that, and it resulted in the Hubble Deep Field. So here we are, Harry Ferguson, Mark Dickinson, and myself, and a group of about 12 others at the Institute crafted this program over 9 months. We announced our intention to do this to the public, and I can tell you now, I never said it too much until recently. In fact, Kenneth Chang, who's a science writer for the New York Times, on the occasion of this week, the 25th anniversary, just emailed me last week, having heard about this, and asked if I would give my perspective on this. And so just yesterday, I submitted to him something that you may see in the Times this week about the meetings I had with Lyman and John DeCall, who visited me on their way down to Washington and basically tried to talk me out of doing the program. In any event, we went ahead because I told them it had to be done, and I was prepared for if there was a negative result to fall on my sword, and I was. In any event, to make a long story short, 150 orbits, the Hubble Deep Field. This is the image that resulted. It is the size of a grain of sand held at arm's length, and it contains 9 stars, 4 ground stars in their own galaxy, and then lots of other little things that represent galaxies, some of which are larger and brighter than others and closer to us, and then other faint things that go back to 90% of the time to the Big Bang. So here you have a core sample of the universe that, if we can interpret it, helps us determine the evolution of the universe, because we're looking here at the basic structure of the universe. So, if you take a detailed image of, a snapshot of some of the larger galaxies in that image, you see this more symmetric feature that galaxies in the current epoch, the present epoch, have. But if you look at the really faint ones, you tend to see what Mark Dickinson called garbage galaxies, or train wrecks. That is, smaller, less luminous, asymmetric things. So to zero order, basically what we're seeing here is the buildup of the structure of the universe from times a couple of billion years after the Big Bang to the present epoch. And it is a really hot topic of research now, exactly how one explains objects evolving from this to this. And mergers, gravitational attraction, it causes these things to merge together, and then something called conservation of angular momentum that eventually produces larger, more symmetric galaxies. So, it turns out this is interesting stuff. And there has been a cottage industry of deep fields that have followed that original study. And I thank Garth Illingworth, who's with us from the University of California, who's with us in the audience, who just gave me this slide. You can see here that after the initial deep field, which actually was put out in 1995, here is a whole sequence of subsequent deep fields, different parts of the sky, using the newer, better instruments on the telescope, using different wavelengths. And so, in fact, there are all of these now newer, different deep fields that have helped us increase the sample size and different parameters to piece together exactly how structure is formed within the universe. So all of these deep fields have produced things just like what you saw, in addition to other interesting phenomena, right? We always like to show these pretty pictures. So here's a pretty picture. And part of the deep fields have elucidated the nature of what are called gravitational lenses. That is, what you see here, gravitational arcs that in fact are lensing produced by a massive object, here a massive galaxy, of a distant object. And you see, in fact, this so-called space-time warp, right? Einstein, through general relativity, demonstrated that the path of light would be changed by a strong gravitational field. And you see the effects here of this distant object that has been imaged here, just as you would image a distant light source through a lens. And so the interesting thing is, it isn't just that it produces a pretty picture, it actually amplifies the brightness of the object, just as a lens does, and enables us to study more distant objects. And so if you're trying to look back in time, and you want to look back as far as you can, and you're limited by the brightness of the object and the ability of the telescope to detect it, using gravitational lensing of distant objects is one of the best ways to get back as far as you can to try to determine exactly what the first structures that formed look like. In any event, some really nice examples of distant objects whose shape is being distorted by the gravitational influence of foreground objects in these gravitational lenses. Now, I won't take the time that I'm tempted to here to explain this, but basically gravitational lenses are explained in this cartoon here, this diagram, where you have a mass of gravitationally bound objects in a cluster of galaxies that essentially are amplifying the light of a distant source, and we observe these arcs here with the telescope. One of the interesting things that one can do with these arcs is you can use the gravitational lenses to map the mass here that is producing the arc. And that may sound like, what's the big deal, right? The fact is, it is one of the primary sources of evidence for the existence of matter that does not interact with light, because we don't see it, but we infer its existence from the gravitational arcs. And here I have a map of one of the best that has been done recently, where you have an image here that's taken with the Hubble telescope where you see these galaxies. And then this blurry stuff is the mass that we infer in that cluster of galaxies from the gravitational lenses that have been imaged with the telescope. So we don't see that material. It doesn't interact with matter, which is why we call it dark matter. And so this is the primary evidence. There is a bunch of stuff out there that is unlike any of the stuff that we're familiar with, because almost everything that we're familiar with interacts with light. It absorbs it, it emits it, it scatters it. but not this stuff. And so one of the great mysteries in astrophysics these days is, what is this stuff? And the short answer is right now, we don't know. Lots of theories, but this is really fundamental, right? By far the greatest amount of mass in the universe is this stuff, but we have no idea what it really is. In any event, the most recent deep fields are, my last slide here, shown in these two figures. Again, Matt Mountain, who will follow me here, and Jennifer Lotz have undertaken a program with a telescope that actually is much grander than the original deep field, which was only 150 orbits. They've got hundreds more. And here you see an image of a cluster of galaxies that in fact is magnifying the light of stuff behind it. And we are hoping to see even more distant galaxies whose lensed images should lie on these contours here, and there's a tremendous amount of work going on right now to identify these, hoping to get us back another billion years closer to the Big Bang time than the image that I showed you that showed 11 billion light years distance. In any event, the deepest image at this point ever taken that is actually a concatenation of some of the previous deep fields is shown here again from Garth Illingworth, and the so-called extreme deep field, right? There was the original Hubble deep field, there was an ultra deep field, there was an extreme deep field, and so pick your name, there will be that, and these are the frontier fields, so the super duper is probably yet to come. And here's an example of where we stand now with the most deep field so far. And so it's the study of these things that is helping us piece together this formation of structure in the universe and how we got here. And if that ain't important, then we're in the wrong place. So, Matt, take it away. Thank you.
So, good evening. So, I helped put this together, and then I wondered, which telecom did I miss that I got to talk about cosmology at 10 past 9 at night? So, cosmology is this subject, and what is it? And I thought, well, let's see if we can. This is actually discussion of some of the most profound discoveries that Hubble has made. And so I thought, go to Wikipedia and look up where the words came from. Philosophical side, well, it's an ancient word. It's formed from the Latin and the Greek, and comes together, and it's really the science of the origin and development of the universe. And Hubble actually originally was designed to investigate the origin and the development of the universe. And so that's what I'm going to talk about. You're building on what you just heard from Bob and the fact that John was able to go up and get fixed. A lot has happened in our understanding. And you can see how our knowledge of the universe has actually been transformed. And of course it starts with Hubble. Here's the animation. We know the universe is expanding, why we called it after that. And as the universe expands, it stretches the fabric of space and time and causes galaxies to actually be redshift. So by their color, you can actually tell how fast they're going, or how fast the universe is expanding. And I forgot to set the clock. Never mind. Just get a sense of scale. Here's the picture of our own galaxy. It's 100,000 light years across. It's a computer projection in the infrared. Just think how big this are. We're roughly 30,000 light years from the center. Even if a spacecraft traveled at 20,000 at the speed of light, it would still take us 20,000 light years to get out there. The fastest object we have is going at roughly 40,000 miles an hour right now, whizzing past Jupiter, in fact. That journey would take us 300 million years. So Hubble is the only way to look at other galaxies in the extragalactic universe and look back in time. And we were able to take pictures of galaxies. This is with a big telescope on the ground, the early days of plates, 25 million light years away because of the light travel time, as Bob said. We can look even further, 70 million light years away. And the galaxies, as Bob said, inhabits the whole universe, and here's just a collection at different distances. And I think to put in perspective what Bob has just told us about the Hubble Deep Field, each one with 100 billion stars, imagine this pinprick that Bob initially started and stared for 10 days in a point of light roughly like a drinking straw, looking through a drinking straw at a single dark point in the sky, getting into trouble from our senior colleagues that he would see nothing, and of course saw this is actually the ultra deep field. Now if you calculate how many drinking straws across the whole sky there are, how many galaxies are in this image, you immediately know there are 200 billion galaxies in the observable universe. That's the scale change that Hubble brought about. By the way, each galaxy has 100 billion stars, and you can do the maths, and it's 10 to the 22 stars in the observable universe. And if you look back in time, because we have this time machine, because of the speed of light, and you zoom in further and further and further, you can see these red dots, and in fact, some of the deepest fields here, you can see light coming from 13 billion light years away. Because as the universe stretches, we get this redshift. So it's exhibit A in this story, because cosmology is about making measurements, not just pictures. We can measure a velocity. So you've got a velocity of every object you see. For many years, even Hubble knew this, there were these objects called Cepheid variables, and here's an image taken with Hubble, the very famous Cepheid variable. The pulsation is actually proportional to the brightness of this object. And there's a relationship between the rate of pulsation and how bright it is. You know by measuring the pulsation of how intrinsically bright it is. And so, for example, if you're driving down the freeway, you know that very faint stars, very faint headlights are a long way away because everything's the same brightness. So if you've got a way to calibrate the absolute brightness of something, what the standard candle is, from measuring the pulsation, you can make measurements of distance independently of velocity. And that was one of the key projects that Hubble first started. Before Hubble was launched, people used to have fistfights about the age of the universe. We disagreed by factors of 2. And astronomers get very excited about things like this. Wendy Friedman led a team that looked at a bunch of these Cepheid variables in other galaxies. So we're doing more what Hubble did. And so with these standard candles, by measuring the variation in brightness in other galaxies, you get a distance. So now you've got a velocity and a distance. Actually, you don't need calculus to do the next calculation. Because time is distance over velocity. So we've got this Hubble Deep Field. You can measure the actual time to each galaxy and get an actual measurement of the history of the universe. And this is what they found. We found, by making that measurement, that the universe was 13.7 billion years old. And the great galaxies were made up and formed from the primordial gas that formed over generations and built up the universe we saw today. So that was the result of that observation. But of course it didn't stop there. Because when you go on these journeys to make what you think are simple measurements like how old the universe is, you discover things you didn't expect. So over the course of all the surface emissions, and here's a compilation of the whole thing.
And liftoff of Space Shuttle Columbus. Liftoff of Space Shuttle Columbus.
Each one of these missions allows us to put more and more sensitive instruments into the Hubble. And we first began to see things with new cameras, which you saw from Bob, these strange objects here. You know, what was going on here? And as Bob tells you, we were discovering dark matter. And what is dark matter? Well, if you're in Baltimore having a drink in the harbor and you see this happening, what actually is happening is a small black hole is going past and bending the light. And of course, we see this in the gravitational lens, as Bob explained, and it allows us to measure with high precision how much dark matter there is. And as Bob said, we discovered that a lot of matter in these clusters of galaxies are actually dark, because you can actually make a measurement. And you can actually see when clusters collide like this, what happens. The red stuff is the hot gas from X-rays. As two clusters of galaxies collide, and as you might imagine, things get pretty hot, tens of millions of degrees. The blue stuff, from the gravitational bending, is clouds of dark matter that are just passing by each other and not interacting at all. So you can see the non-interaction of dark matter. So what you're seeing really is what you might see at night. This is our view of the universe. This is the US. Now you know there's a lot more to the US than this. But what we've discovered over the course of time is that this is all Hubble is actually seeing. And underneath is this whole superstructure of dark matter. And it isn't just in individual galaxies. This is what we thought our picture of the universe was, galaxies flying apart, great big spaces between these galaxies. And as you look at the physics of what's going on, you actually, this is animation, you realize the whole universe is filled with a network of dark matter, a sort of lattice work that came out of the Big Bang, and the galaxies are just the tips of the icebergs of this massive structure. And you say, well, that's all really nice, it's a very nice computer animation map, but how do you know this is even real? Well, Hubble can see this lacework. Not in the same way, but in the last servicing mission, we launched a very sensitive ultraviolet spectrograph, who looks at a very distant object called a quasar, which is just a point, a very condensed object, very bright in the ultraviolet, and we can look at the light passing from this quasar, and as it goes through each one of these filaments of dark matter, real matter is captured in it, and a little bit more light is taken away, and we can actually see elements in between galaxies. We can see that cosmic web and matter trapped in the intergalactic medium. And there we go. Here are some filaments in the ultraviolet, and we can actually see oxygen and hydrogen trapped in that interstellar, intergalactic medium from that filament. We can see dark matter pervading the universe, at least the image, the faint trace, visible trace, or the ultraviolet trace in this thing, of an underlying substructure of dark matter. And as you look further back, with each mission, you can get greater distances. And so here was how much matter is in the universe. Simple question you give your graduate students to do. Because it's a boring problem. The answer is interesting. So there is Hubble's diagram, and that's how far Wendy got. And then each servicing mission allowed us to go deeper and further back. There's the distance, and there's the redshift. And of course, we expected a straight line, and the gradient would give you the amount of matter. The problem was, it didn't quite work out that way. Because you see those red dots don't quite fit the red line. That's a problem, because that wasn't expected. That wasn't supposed to happen. The universe was supposed to be explainable. The people who did this stumbled over something called dark energy. Every time you hear the word dark, it means we don't know what it is. And here was the prevailing picture of the universe. The Big Bang, we didn't know how much matter there was. If there was a lot of matter, most of it dark, we now realize the universe would expand, the matter would contract in, and it would have the great crunch. Or the explosion would be big, but there wasn't enough matter, it would just keep flying apart. And so you give your graduate students the job of trying to work out what to do. And we could use standard candles in different ways. Supernova that explode are very bright. We found a way, at least the groups found a way, to use supernova, those standard candles, which you can see halfway across the universe. A bit like these Cepheid variables. But supernova blow up in a very predictable way. So if you see a supernova, you know how bright it is, you can measure its dimness and then calculate its distance independently from its redshift. And here are supernova taken with the Hubble Space Telescope, 6 to 7 billion light years from here. Before and after are standard candles. So using that simple math, not quite as simple as that, velocity and distance, we can measure time and measure the history of what's going on. And the expansion rate should tell us how much matter there is. And here is Adam Rees's notebook from those measurements taken from the ground. It's like any notebook, any science project you do, here's the testing, the precision, the accuracy, and the answer. There was a slight problem with his answer. How much matter in the universe is there? The answer is negative. Any other person would go, I have screwed up my math. How can there be negative matter? I was supposed to get a positive answer. And of course, what it meant was, actually, the universe was accelerating away from us and giving a false answer. It meant there was an accelerating force in the universe, which in fact represented 70% of all the energy in the universe. And this was the discovery of dark matter, of dark energy. So, out goes those two models, and here comes this really weird model. This is our universe today. I take this pointer, I throw it up into the air. What do you expect? It goes up, it slows down, and it should fall back in my hand. If I really throw it up hard, it should go a bit higher, but it will slow down. What's actually happening in our universe, I throw this up in the air, it goes up, it slows down, and it accelerates through the roof. Now that's pretty weird, but that's what's happening. And here is the discovery graph. It was discovered, this effect was discovered on the ground using ground-based telescopes, but it wasn't until Hubble showed where this effect turned over back in time that led to extraordinary claims, required extraordinary evidence. That extraordinary evidence came from the Hubble Space Telescope, which led, in 2011, to the Nobel Prize to these three distinguished physicists for the discovery of the accelerating universe using the Hubble Space Telescope. In fact, the Hubble Space Telescope was called out in the citation. And, oh, this didn't show. Oh, it did. A distinguished physicist at Princeton points out, or somebody else said, who ordered that? I didn't want it. Either our calculations are wrong by 10 to the 120th, which even in cosmology is a big error, or we live in trillions of universes, or there's someone discovered fifth force. And today, we actually don't know the answer to that question. So, here we are. Hubble set out to measure the size and the scale of the universe using greater and greater tools, more and more powerful. And we got this great picture of the universe, and we are at the end point of this. At least one galaxy we think we understood and are informed. But you see this acceleration going on suddenly through time. And so we're actually left with this picture of the universe. The bit we understand is the bit in green, 4%. We haven't got a clue what dark matter is, 22%. And we know even less about the 74% dark energy that makes up the universe. So Hubble's greatest discovery is that we understand even less than when we started. And so I like to quote Joseph Silk here, that humility in the face of great unknowns is the true philosophy that I will say Hubble has to offer to us tonight. And that's where I will end it, and I'll pass on to Mark about how we take the next steps beyond the Hubble Space Telescope.
Good evening, sir. It's a great pleasure to be here. I wanted to start by just saying that the James Webb Space Telescope was really conceived in the 5 years after the Hubble Space Telescope did the Hubble Deep Field that you heard about from Bob Williams here. And it came to the realization that if we wanted to study the most distant galaxies, we were going to need to move to the infrared, because most of the light from those very distant galaxies would appear in the infrared, and Hubble Space Telescope would not allow us to be able to reach back to those wavelengths. And over this one, start here. So here is the real differences between the next big thing. So you ask yourself, how can you sort of build upon what Hubble's done? Well, you want something larger, something cooler, right? So that's exactly what we're building. We're building a larger telescope, and we're also building an infrared telescope, which means it has to be extremely cold, because we want to image the light, the very earliest objects in the universe, and that's going to be heat radiation. And if we're putting out thermal radiation or heat radiation ourselves, we're not going to be able to see it. So we need to be extremely cold so that we can image the light from these very first galaxies. So that gives us the basic premise for the James Webb Space Telescope. Hubble here. So this is the basic difference between the two telescopes. Hubble is a 2.5 meter aperture, and the mirror is at room temperature. It was built at room temperature to operate at room temperature. And this here basically just gives you some idea of how sharp the images are. So 1.6 microns, which is close to the limit that Hubble can image at in the infrared. Beyond that, it's just swamped by thermal radiation in this room temperature, operational temperature. This is the kind of sharpness you get, and so Hubble can do 120 nanometers ultraviolet all the way out to about 1.6, 1.7 microns. Instead, we go to JWST, and JWST is a 6.5 meter telescope, and it's going to operate at 40 Kelvin. So that's 40 degrees above absolute zero. Now you can put one of these in a fridge, and it's going to stop working, you know, when it gets just around 0 degrees C. So building something that is going to operate and function 40 degrees above absolute zero is a real challenge. But that's what we need to do. Now that large aperture in the infrared at 2 microns gives us this kind of sharpness, and then at the far mid-infrared range is going to give us image sharpnesses that look like this. And James Webb Space Telescope will basically operate from 0.6 microns, which overlaps with Hubble, and operate all the way out to 29 microns. Now there's another big difference. It's going to be operated at a place called the second Lagrange point, or L2, which you can see here, which is about 1 million miles from the moon. So you start at the sun, you draw a line to the Earth, keep going for 1 million miles, and there's L2. And this is a sort of quasi-gravitationally stable point. And we actually orbit it because we don't want to be in the shadow of the Earth, or we have no power from the sun. Hubble instead is orbiting in a low Earth orbit around the Earth, and that means that 45 minutes of its orbit is in the dark and it's doing science. Then it goes through night-day terminator, and it's in the daylight, and it has to do internal calibrations, and then it goes back into the dark again, going through the terminator again. So it's not a very thermally stable environment. You know, 45 minutes you're getting baked by the sun. The next 45 minutes you're in the dark. So it's continually heating and cooling. And this actually causes something like a 3 micron focus change in the optics of Hubble, which for a 2.5 meter telescope is not a big deal. For a 6.5 meter telescope, it's a showstopper. So we don't want to be in low Earth orbit. We want to be out here where we're not going around the Earth, and we're in what's essentially a thermally benign environment. It also gives us another big advantage, which is that we can do 24/7 science. We're doing science all the time, except when we zoom from one object to the next. So we're much, much more efficient. So this is how this telescope works. It's a complete paradigm change from the traditional mirror in a tube that you see with Hubble. Hubble's designed to be in low Earth orbit, so it has to worry about stray light from the Earth, and that's why it's in that big long tube. This telescope instead has to worry about being cold, and the way we deal with that, rather than flying the telescope with a big dustbin full of liquid helium, which boils off in a couple of years, we instead went with a brand new idea called passive cooling. And that's what these membranes here provide. So you'll see these again later on in the talk, and I'll show you how they work. So the basic idea is we have the telescope here, primary mirror, secondary mirror. Light comes in off the primary onto the secondary through this baffle here into the science instruments, which are located back here. And everything on this side is cold, 40 Kelvin, and we keep it cold for the lifetime of the mission. Everything on this side, behind these tennis court-sized membranes, is hot and basically looking at the sun. So we have this big box here, which is the spacecraft bus. Has all the usual electronics you need, communications, propulsion, all that kind of stuff. And that operates on the warm side of the telescope. So that's the basic idea behind this telescope. You keep essentially all the optics and the instruments in the shade, let them cool down, and then they'll sit there at 40 Kelvin and operate at a temperature where we can do infrared science. Now there's a couple of gotchas here. One is that you have to move this whole telescope off of the bus, because the bus is operating at room temperature, and you don't want your telescope attached to a large hot object. So we also have a tower here which separates the telescope from the hot bus. The other big gotcha is that you have to align this telescope in room temperature to be optically aligned when it's at 40 Kelvin. So all the mirrors, you have to do something called cryo-polishing. You have to polish the mirrors at room temperature, measure them at 40 degrees Kelvin, and then figure out what you have to polish back into them again at room temperature, so the next time when you pull them down and you finish polishing, you've got the right surface figure on these mirrors. So it's a big alignment challenge, this telescope. The other big challenge is it's too big to fit in any fairing. And so we have to stow everything for launch. And that means that we have what some people have called a transformer telescope or an origami telescope, you name it, it's been given a name. But the bottom line is we have to fold everything up, including the mirrors. So the secondary mirror here gets folded up. You can see it's just here. The primary mirror is segmented. It's not a single piece of material. It's actually made of segments, and the segments can be folded around the side of the telescope. So you can see it's made of 18 segments. 12 of them are in the main section, and then 3 on each side actually fold around the side of the telescope. And then we basically roll up these big membranes onto these pallets you see just here, and they are locked to the telescope. So this is what it looks like when we launch it. And once it's launched and it's on its way to L2, everything's got to be unpacked again. So this is the big engineering challenge of this telescope. And it's a successful deployment, and I'll show you why we think we've got that under control towards the end of the talk. We also have a really nice set of science instruments. Hubble showed the importance of having really good, efficient, and well thought out science instruments. This is what we are going to fly on this telescope. So to do the very deep imaging programs you've been hearing about, we have the NIRCam, which is built at the University of Arizona. That will give us deep wide field imaging. 2 simultaneous cameras. This one gives us 1 to 2.5 microns. And this one here is the 2.5 to 5 microns. So we have a dichroic that actually splits the light so that we can do the 2 fields simultaneously. It's also the telescope that does this thing here. WFSC is NASA's for wavefront sensing. Basically, it's a segmented mirror. So once you get it into orbit, you've got to move all those segments until you've got a perfect mirror. And we do that basically using a technique we developed to understand the spherical aberration on Hubble. So what goes around comes around, and we're actually using what we learned fixing Hubble to actually phase and align this telescope once it's on orbit. And then finally, we also have on this camera a coronagraphic imager. This is for studying the disks that you heard about earlier, and generally they're around bright stars, of course, and you need to block out the light from the star before you can actually image the disks. So if you want to know how these instruments work, if you just look at a light on the ceiling and put your thumb over the light, that's basically what we do. We block out the light from the bright object, and then we can image the regions around to see what's there, hopefully a disk. Then we have a European object instrument. I'm going to come back to this, but it's basically designed to look at very faint objects and obtain spectra of them, disperse them using either a prism or a prism. We can actually do 3D spectroscopy, which means we take an image, and for each pixel in that image we get a spectrum, so we can build up a very complex picture of what's going on in the centers of galaxies. And then we also have the traditional long slits. Then we have a mid-infrared instrument, which provides us with wide field imaging in the mid-infrared, 5 to 30 microns. And again, spectroscopy and coronagraphy to do the high contrast imaging. And then finally, the Canadian instrument, which provides us with a way of removing jitter. So the spacecraft cannot hold the telescope still enough to get the perfect image quality that the mirror will deliver. So you have to have a way of removing the residual jitter, because the spacecraft bus is always shaking a very small amount. And we have a tilt mirror in the optical chain, and the Canadian instrument measures the jitter from the guide star, feeds that to the tilt mirror, and that removes all of the jitter. So it's kind of like the image stabilization on your digital cameras, except on a grander scale. And then we also have some more spectroscopic capabilities on this instrument. And then stuck in the middle here, you see all of these instruments finished, completed, and integrated into the structure that holds them, or the skeleton that they're bolted to, ready to be tested. So, JWST is designed to be a facility observatory, just like the Hubble Space Telescope. You know, we're not building this to do one problem. It's supposed to be an observatory that will present a range of different capabilities to facilitate science by a large part of the community. The primary science goal that motivated a lot of the design was first light and the reionization of the universe. This is understanding the very most distant galaxies in the universe, and I'll speak a bit more about that. You already heard from Bob Williams that understanding the difference between the most distant galaxies and more nearby galaxies, or a problem that we call the assembly of galaxies, is very important. And then closer to home, we're going to be studying the birth of stars and protoplanetary systems in these dark regions that you heard about from Jennifer, and also studying exoplanet systems and the origins of life. So I'm not going to say too much about the first light problem. I think there's been a lot of discussion of this tonight already. But the basic idea is that Hubble can take us back to something like objects a billion years after the Big Bang, which is somewhere in this region here. And we really want to be able to image back to the epoch when the very first stars and galaxies formed. And we think that's probably in the sort of 300 to 400 million years after the Big Bang kind of time frame. And the light from those galaxies is going to be predominantly in the sort of 1 to 5 micron bandpass. So we will do these studies to answer these very important questions here by essentially continuing the work that Hubble has done. We will be going back, revisiting those Hubble deep fields, taking extremely deep observations with the James Webb Space Telescope, and we'll also be using these new frontier fields that have been established by Matt Mountain and the team at the Space Telescope Science Institute to continue these studies beyond just the Hubble deep fields. And the kind of things that we will get, you've seen lots of really nice images tonight, but basically what they get turned into are plots like this, and these are all from a paper by Richard Boons and Garth Illingworth, basically just understanding how the numbers of galaxies, the function of brightness and their luminosity evolves. And you're basically doing these surveys to find the candidates that you want to follow up and identify as the very first galaxies. And also, of course, the evolution of the star formation rate, studying how that varies as a function of redshift. And then you want to follow up these objects and get spectroscopy. And I talked briefly about the multi-object capability. The way we do this is by using nanotechnology. It takes a very long time to get one spectra of these extremely faint objects. So we want to do up to about 100 at a time to really leverage the power of this telescope. Now, with a traditional fixed slit, you can't do that because you put your object in the slit and then you send the light off to a prism and you're pretty much done. So we needed to find a way to be able to pick off 100 objects in the field without necessarily knowing where they were going to be. And what we came up with was this microshutter array, and you can see it working here. And basically it allows you to open a set of shutters anywhere in the field so that you can basically identify your candidates and then program the spectrograph to go away and study those. So if you just happen to have a set of high redshift candidates lined up in the NASA logo like that, you'd be all set to get your spectrum. And when you do that, basically you end up with a set of data that looks like this. Each one of these is a spectrum of a galaxy. This is actually a simulation. So it's a very nice way of leveraging the power of this telescope as much as we possibly can before we even started to do science. Coming into our own galaxy, another important science area is the birth of stars and protoplanetary systems. Really understanding how stars form in dark clouds and how the environment in those clouds affects how they're born and evolve. And the way we would do that with JWST is using that infrared capability to peer into these dark clouds. You saw missions like Spitzer have been able to already identify stars. We can, inside these clouds, we can use each of these stars as a probe to study the material, the gas that's in these clouds. And then, as you heard from Jennifer, we really like to be able to study a lot of these objects in these dark clouds and understand step by step how disks form, what are the conditions for disks forming around young stars, and what are the conditions for them surviving and evolving into a planetary system or getting destroyed by their environment. And by using the new angular resolution that we will get from this telescope, given by this really large mirror, combined with these fantastic spectroscopic capabilities that allow us to span 1 to 30 microns, where most of the key molecules have emission or absorption lines, we can really start to take these kind of objects apart and figure out what's in them, how they work, and how the star and planet formation processes are working. And then finally, this image here just shows the power of JWST. This is the Hubble Space Telescope image of the formal Hubble disk, and you see a nice ring of scattered light here. This is the Spitzer 24 micron image telling us that yes, there's a point source, which is formal Hubble, but there's also something else there. But we don't quite know what it is because we're not really resolving it. Spitzer was a relatively small telescope. But with JWST, we'll be able to start to really understand these debris disks, the last stages of this sort of evolution from these disks up here through these phases to a cleared out system with perhaps debris left afterwards, as you see here in formal Hubble, and of course as we have in our own solar system. One of the key areas that this telescope will really excel, in my opinion, is in studying exoplanets. You've heard a little bit about that already tonight. I'm not going to talk about imaging, but I'm going to talk about transit science. And this is basically studying exoplanet eclipses. So if you think of traditional eclipse, what's happening here instead is that the planet goes across the face of the star. You see a very small dip in the light. If you're looking in the mid-infrared, which only JWST can do, you actually see the dip when the planet goes behind the star. And this allows you to start to do really interesting things when you disperse that light. You can study by doing emission spectroscopy when the planet goes behind the star, the composition of the atmospheres, the temperature, pressure profiles of the atmospheres of these planets, study the global energy budget, and also understand the nature of clouds. And then if you study the transmission where the planet's going in front of the star and the visible in the near infrared, again, you can study composition, clouds, and you can even start to estimate the planet's mass just from these observations. And so that takes us to some very interesting things that we can do with this telescope. Comparative planetology. So you saw a couple of examples that Jennifer showed of observations of gas giants. One of the problems we're seeing with the Hubble observations is a lot of these planets have very cloudy, hazy atmospheres. And when you look at them in transmission with Hubble, you can't really see that much. They have very grey atmospheres. With JWST, we can go all the way out to 30 microns, and in the 5 to 30 micron region, we can penetrate those clouds and hazes and really start to understand the nature of the atmospheres. And these couple of simulations my colleague Tom Green at NASA Ames did, showing how you can really start to do solid atmospheric chemistry, understand the role of clouds, you can get access to all these features. So the dark lines are the simulated observation, and the red line is the spectrum. So you really open yourself up to being able to study a lot of different features in these gas giant spectra. You can also start to study the weather on planets. So another important thing that Hubble has started to be able to do is what's called full-phase spectroscopic mapping. So you don't just study the transit, but you study the whole orbit of the planet around its star, and you study the light that you get at each point in that orbit. And you actually, in addition to the transits, can see for the very short period ones the variation of the the planet's emission is a function of orbit. And then you can break that out into spectra, and you can see this water detection here, which comes and goes as a function of phase. And then you can build circulation models. So this is a circulation model, or a very basic weather model for HD 80606b, which was put together by Greg Locke. So not only can we study weather on our own planet using NASA missions, we can now study weather on exoplanets. And then finally, the big question we always get asked, what about Earths and super-Earths? Well, we're still trying to understand what the ultimate limits of observations using transit spectroscopy is going to be. But one of the big areas where we think we'll do really groundbreaking observations is studying super-Earth atmospheres and really trying to understand whether we can see potentially biosignatures or evidence that there might be life on these planets. And this is a simulation that one of my colleagues on the Canadian team did using a model from Lisa Kaltenegger. And this is an Earth analog planet orbiting an M-dwarf. And you can see that in this simulation, you're able to detect water, oxygen, carbon dioxide, and methane here at 2.4. Some of the key things that we're interested in that we're trying to understand whether we have biosignatures. Now, the issue here, or the key, is that you need a lot of transit. So we have to find systems with transiting super-Earths or Earth-like planets in the right part of the sky, where JWST can keep coming back time and time again to collect enough data to do these kind of observations. So there's a lot of really exciting science coming with this telescope that's going to do really new and groundbreaking work in some of these areas. So final couple of charts, let me just address where we are with the telescope, because people always want to know, where are you? Are you going to launch on schedule? And the answer is we are making really rapid progress getting this telescope built. And what you see here is all flight hardware. So we have flight instruments mounted in the flight ISIM, which is this sort of black structure that they're bolted to. This is the final flight telescope structure, the center part of the backplane, the wings, the secondary mirror support. This is just being finished up Northrop Grumman right now. They're just doing the final stages of alignment. We're building flight sunshield membranes. This is the tower that lifts the telescope off of the spacecraft bus so that it can cool down. This is the spacecraft bus. Now, it doesn't look like a box, because in the heart of that big box you see is actually a big composite cone, which is the main load-bearing structure, and then we wrap around that for the electronics boxes. This is the Arc Optics bench, and this is one of the telescope mirrors, and we have all 18 flight mirrors and the flight secondary sitting on the shelf at Goddard, waiting for this guy to arrive at Goddard in August, and then we'll start putting the telescope together. So at the end of this year, in December, you'll be able to go to Goddard and look through the window of our big clean room and see a finished telescope. So we're really making very rapid progress. So I will finish up there by just saying that JWST will build on the legacy of Hubble, do really transformational science. It's going to change our view of the universe, and we are still on schedule for a 2018 launch. And I will finish there and just leave this video, which just shows one of our first ground test deployments of these sunshield membranes. So I like to think of these as the largest candy wrappers in the world. It's basically the same kind of material you make birthday balloons out of, and there's 5 of them. So first we pull them out, and then we have cables that separate them so that we can achieve the correct thermal performance. So I will leave that running, and yeah, you heard about the grind of hard work. These guys are working really hard. Thank you.
For one of our microphone runners to find you and give you the microphone. When you get the microphone, please stand up. Tell us your name. Tell us if you are a member of the society or guest, and ask a question. Speeches are reserved for the discussion period after the question.
I'll go now.
So if you have a question, please raise your hand. And all the speakers have their mics on, so we get some good feedback. You have a question?
Yes, I do. But before the question, H. Geiger Sievers in 1962 told an incoming freshman at Carnegie Institute of Technology that American colleges are full of knowledge. The freshmen bring a little bit in, the seniors take none out, and knowledge accumulates. And the question has to do with this increase of knowledge. Even when you have the spherical aberration problem, I believe that led to an increase in knowledge on corrective optics. And can anyone tell us how much it helped in that entire field of corrective optics?
I can take that one. So I think it helped us in two areas. One, corrective optics, but I think more importantly, the software, mathematical techniques to actually generate the corrective optics. So it led to a major area of development called phase retrieval. And phase retrieval is a very well-used technique now, but at the time it wasn't that well developed. And we really spent a lot of time developing techniques like phase retrieval to really understand spherical aberration on Hubble. So yes, software I think was the most important part. We also learned how to make very precise corrective optics.
My name is Bruce Murray. I'm a guest. I attended the National Mathematics program down at the Smithsonian on Saturday, and one of the speakers talked about the possibility of there being an extra, it sounded to me like a spatial dimension in the general theory of relativity. This was a hypothesis which gravitational lensing was perhaps a way of exploring, looking for shadows. Is this related to this possible fifth force that was spoken of?
Sorry, cosmologist here.
So I think, let me just talk about certainly gravitational lensing. What that has done is shown how well general relativity works. So that's not, I mean, where people think dark matter, the solution to dark matter exists is where this collision or discontinuity in description universe for quantum mechanics and general relativity, where those cross over, we don't understand what's going on. And the belief is that trying to understand dark matter may give us insight into what's going on, where those two ideas collide in a vectoric pattern. Fifth force is just one of the ideas as a solution to what may be going on with dark energy. Has to be the fact that we're just one of trillions of universes too, which is a principle of the universe is because we are. So I think that's all I know really about this. I don't know, but certainly not in the calculation. So I mean, one of the powers that we've discovered, because we've been able to calibrate this using supernova, is that general relativity works exceptionally well at high precision with these calculations of these cosmos plans. And every time you switch on your GPS, you know that general relativity works really well.
I'm Bob Hershey, I'm a member. What kinds of things can be done by the Hubble and the JWST working jointly when they're up there together?
Well, I'll say a few things, and then maybe Mark can say a few things, or anybody. One is if there's some transient phenomenon, something that happens that we can actually monitor its changes over time, like a supernova explosion or something of that nature, it would be very, very good if we could have all of these wavelengths of light monitoring that phenomenon at the same time. So we don't have to second guess how these things fit together. So Hubble can look visible light and ultraviolet light and near-infrared light, and then JWST can look farther into the infrared. If we can have all that information together and really help us, I think that's Same is true for even phenomena in our own solar system, looking at planets, transitory activity on the planets in our solar system. It'll be great if we can have both telescopes operating together. But Mark,
not only Hubble and James Webb Space Telescope, but we are about to enter at least a decade of astronomy that will be unparalleled in any time in human history by a large leap, not an incremental change. But it is having Hubble, the James Webb Space Telescope, but also the Atacama Large Millimeter Array, which is the Hubble above ground-based radio astronomy. And these very large telescopes, like the 30-meter telescope, which are being built at about the same time. And these are focused, we'll be able to look at single objects, whether it's an exoplanet or a galaxy or something in our own solar system. But also we're working on telescopes that are going to not be very narrow field of view, but very large field of view. And they're going to spot new things that we would otherwise miss. And there's one on the ground. It's called the Large Synoptic Survey Telescope. Hopefully they'll reinvent that name. And one in space that's going to be called the Wide Field Infrared Space Telescope, WFIRST. Also, I hope we come up with a new name for that. And those will be in the same time frame as these wonderful exploratory telescopes.
One of the interesting things that has emerged in astronomy in the past 2 decades, I would say, is multi-wavelength astrophysics. And it's because each one of these missions samples different energy regimes. An X-ray, you can add on the NASA use the X-ray telescope. So it is important to sample at the same time all of these different regimes, and you have to use different facilities, different telescopes, some in the ground, some in the space to do it. And the increase in knowledge you get from doing that is huge, right? The classic trying to understand an elephant by just looking at one part, so you've got to sample all the wavelength regimes to try to piece together exactly what the phenomenon is that you're looking at.
Gentleman in the orange shirt here.
My name is John Birch. I'm a guest. I have been intrigued by, well, you mentioned something about the quantum overlap. Yeah, overlap between quantum and relativistic physics. And I was wondering if anybody has a feel for the proportion of mass in the universe that might be these boiling virtual particles, and whether that may have something to do with the way in which these filaments form across the universe.
Well, I'm an observer, not a theoretician, but that number, that 10 to the 120th, if they do the calculation of that boiling filament, they get this number, which is wrong by 10 to the 120th. I think the simple answer is we don't know.
We have 2 questions in the back and then one in the front.
Hiden Matsumoto from NHK TV Japan. We are now producing a documentary about 25 years of scientific achievements of the Hubble Space Telescope, and that's the reason we are here. This is a question to Dr. Williams. I understand when you proposed the original Hubble Deep Field, some people thought that was a great idea, but others thought that was a crazy idea. And I understand that you took the risk to use the discretionary time as a director to do the project. In that sense, you took the risk. Looking back in retrospect, how do you feel about your decision to take the risk 20 years ago?
Well, we all screw up once in a while. Well, that's a question that I get asked the most often, of course, about the deep field. And the only thing I can say is that one man's treasure is another man's garbage. We all, how does one perceive these things? To me, it was obvious. It had to be done. And I'm a risk taker. Always have been a risk taker, and I think that you would get most people who are scientists agreeing that taking risks is really important. But of course, when you're dealing with expensive projects, you have to be aware of the political implications. I was in a position where, as I mentioned in my talk, it just wasn't important to me. Because of science, it had to be done. And nothing profound about it. I looked upon this in a different way than John McCall did. And I would defend, actually, John. I must say that in our conversations, and he did spend several long afternoons with me, trying to talk me out of it. But it was always very professional, very cordial. And I told John I understand why he felt that way, because the ramifications could have been very important, right? After the servicing mission, this is one of the big things. If we came up empty-handed, boy, what a bunch of dummies those guys were. But I was prepared to face that. Really, you got to do it. So what can I say? Yeah, and of course, I'm very pleased that it worked out. But the fact is, it would have been a very interesting result, even if we'd come up with very little.
Just more difficulty.
Yeah. Yeah. So I believe really the story that comes out of this is the fact that one really must take risks. And when you're dealing with something that is expensive, you do need to think of the default off-ramp you have to take. In my case, it was one guy made a bad decisions, and I really believe that, and I told this to John, I believe that the recovery would have occurred on a short time scale. So.
Could I just add something to that? Because Galileo talks about a world on paper, and not you should explore the real world. You shouldn't be so concerned with the world on paper. And if people had believed the predictions about X-ray astronomy around about 1960, nobody would have ever done X-ray astronomy. And so it was basically building things with new capabilities and looking. But it seems to me, has in many ways been the central driver in the history of space astronomy, rather than relying on the theoreticians whose record is pretty, well.
Gentleman there?
Yeah, hello. Tad Daly is my name. I'm a political scientist, not a astrophysical scientist, and happy to be a guest of the Society. It's possible that I misheard, but I thought I heard Jennifer Wiseman talk about Hubble searching for signs of life, and I also heard the word biosignature. But then I thought, again, maybe I misheard, I thought I heard you, Dr. Clampin, talk about the Webb telescope maybe teaching us about the origins of life. My understanding is that the biologists understand about as much as the origins of life as you all do about dark matter and dark energy. So what in the world can a telescope, even one as jazzy as the Webb, teach us about the origins of life?
Could I clarify what I said about Hubble first? And then,
please.
So what I said was that Hubble is helping, we're taking first steps with Hubble in understanding how to analyze atmospheres of a few of these extrasolar planets that happen to be orbiting in the right geometry for them to transit in front of their parent stars. And we can look at what kinds of absorption takes place in those atmospheres. We can identify some very interesting elements, including water vapor. None of these are even close to giving us what we would call evidence of biological activity on those particular planets, but they're stepping stones. And there's a very hot field of astrobiology right now that's helping us understand what kinds of evidence we could see remotely that would tell us on perhaps what we might call a habitable planet that there might be biological activity going on. I think we are going to need future telescopes to really do that kind of more conclusive analysis. So Hubble is not right now identifying signs of life on other planets, but we're taking those first steps of understanding how you would do that atmospheric analysis in exoplanets. And then Mark, you can explain where JWST picks up.
Sure, so the JWST theme is really focused on two things. So one is exoplanets, planets in other solar systems, and studying those. And then the other part of the origins of life theme comes from just understanding our own solar system, how we got all the water, where did the water on our planet come from, basically the transport of volatiles, organics within our own solar system. So it's really talking about studying our own solar system and then moving out to other exoplanets and studying their atmospheres and trying to understand what's going on there.
Let me just pick up on this uncertainty of biologists. So there's another big number which we went past very quickly. And we calculate there's roughly 10 to the 22 stars. That's 10 with 22 zeros in our observable universe. And if you ask some physicists, they'll say, well, therefore, there's obviously life. I mean, after all, 10 to 22 is a big number. Statistically, we'll find something. However, if you ask a biologist, they'll say, yes, there's a very complex sequence of events that you have to go through, and 10 to the 22 may not be enough. So you have these two sides, and the difference is 10 to the 22, which I will claim is actually better than being wrong by 122. And the only way we're going to resolve this is by observation, which is back to the original point by Galileo. You know, we don't know how to calculate these things. So by making the observations, then we're ultimately going to know whether or not we're alone.
We're also trying to find out what kinds of planets might be habitable. That doesn't mean that they're inhabited, but what does it mean for a planet to be habitable? What kinds of conditions would be conducive for life to thrive? And we're still at the very stepping stones of trying to understand that.
Of course, you know, it may even be in our own solar system. We know of an example of one, the Earth. We showed images of Europa and possible plumes of water coming out of Europa. Underneath the icy crust of Europa, a moon of Jupiter, is a warm, salty ocean. It's been like that for 4 billion years. And one of the things that astronomy has taught us is that the building blocks of life, you think about those old descriptions of experiments of putting a bunch of inorganic chemicals in a pond and zapping it with lightning, you can create organic molecules. But you don't need to do that. Those organic molecules, all the building blocks of life, are floating throughout our solar system, throughout the galaxy, and by inference throughout the universe. Nature makes those already in those dense, beautiful clouds filled with organic molecules. They're seeded by them. Meteorites are filled with them. Amino acids are in meteorites. And so the possibility that Europa, this warm, salty ocean, has been sitting there percolating with all these organics and heat and water for billions of years, perhaps there's life there. Or Ganymede, or Enceladus, a moon around Saturn, all which have these warm, salty oceans. Or perhaps Mars. We've now detected organic molecules in ancient rock on Mars, but also signals of methane gas coming out from Mars now. We believed for many years Mars to be geologically dead, so where's this methane coming from? Maybe Mars is not geologically dead, maybe it's still geologically alive, volcanism, volcanoes, or magma underneath. Or there's microbes. We see a signal that's correlated with summer. Microbes make most of the methane on Earth, so along with cows. Well, microbes in the cows. But there's also another fundamental question in philosophical society, which is equally as interesting as the question of, are there habitable environments on other planets or moons? But how long will the Earth be habitable for us? And I think that's, in some ways, maybe a more important question, topic of the Lunar Summit.
Carl Darrell, member of the Society. About a year ago, there was a survey of the local universe that was published, and you could see the images, and it was, you could see all the galaxies moving, and it sort of surprised me because we're moving toward what they call the great attractor quicker than we are going around the sun. And the question is, would these little Webb telescope in particular give us any further insight as to what that, quote, massive object is?
That's a Webb question.
Well, so with the Hubble, we are able to make very precise measurements. And we know, for example, as part of the dynamics, that Andromeda will crash into us, we're very careful, in about 4 billion years' time. But there's so much space between the stars, actually, that, the sky make it very interesting. But, nothing, the probability of anything happening to us is very small. And then all these clusters are going to this so-called great attractor. But the structure, we'll probably get a better handle on that structure from the big ground-based telescopes, or this telescope called WFIRST, that will actually make these huge surveys. It allowed us to construct this trellis work that I showed, where we think way dark matter structure throughout. James Webb will look at the individual objects and maybe be able to measure velocities of very high redshift objects. This is very much a local universe. Really, we need more wider field data to answer that question.
Actually, in some of the comments that were made, the real problem is that our place in the galaxy, it's on the other side of the galaxy, so we can't see our own galaxy. We may have to wait until we rotate all the way around.
But we can see other galaxies moving as well out of the plane. I mean, that's the whole point. We can produce this three-dimensional picture of
So the movement toward the great attractor is not a surprise. It is expected. Large scale, the universe appears to be homogeneous, but smaller scale, it's clearly inhomogeneous, and that has to be a large inhomogeneity.
Kristen Perry, and I am a member of the Society, and I can say it's amazing to be having this conversation because 25 years ago, when I was a very junior flight controller in mission control, there were about 6 times during the night where I didn't think we'd have anything but space junk. However, a lot of that has to do with the complexity of something like this, and I wanted to direct something to Dr. Smith. Do you feel like it is any easier or harder to mount such an effort now than it was then?
I would say we have evidence from 3 really big physical science projects: Hubble, the SSC, and JWST. SSC failed. No, it got cancelled. HST had assorted near-death moments, and JWST had its, probably as Garth Illingworth was talking about at our dinner table, it had a death experience in 2011. And so the technical scientific efforts, I think, have to be undergirded by social efforts and social transformations and an awareness amongst the advocates of just what it takes to move to these new kinds of scales and to realize that these projects will take a very long time and that inevitably somewhere along the road there will be big problems. And I think in a way Hubble was lucky in that it had its really big problems early, and so that enabled what I call a coalition of supporters to be assembled, because then that coalition could be brought into the field on later occasions to keep Hubble alive and going. If you try and wait till your death experiences come to put a coalition of political supporters together to get you enough votes to keep on moving for a really big federally funded project, it may be too late. And I think that's what happened with the SSC, because John's point there was, I think, a kind of hubris amongst the physicists. They'd sailed through, they'd not had to really fight hard. Whereas with Hubble, the difference, it seems to me, is that they really had a very hard fight getting things moving initially. But that, in the long run, I think was really very much to their benefit. Now, if you look at something like ITER, which is this transnational project, which has all these massive political problems, massively overrunning, mounting these really big projects is very, very hard. And it's not just the science and technology that you've got to get right, you've also got to get the politics and the social structures right, it seems to me. And so I think fairly recently, Steven Weinberg, Nobel Prize winning high-energy physicist, lamented that what he saw as the end of big science projects. Well, I don't think it's, that seems to me to miss the point. I think what has to happen is that the advocates have really got to understand when they move to these kind of new scales, what a huge job it's going to be to make their project not just scientifically feasible, technically feasible, but also politically feasible.
And to tell a short story, which is I started at the Space Telescope Science Institute on January 4th, 2010. And I took the job working for Matt Mountain as deputy director because I was so excited about Hubble. I'd just come back, refurbishing the telescope, the science was outstanding. And I was incredibly excited about the prospect of the James Webb Space Telescope, which at the time was going to launch 4 years later. And I thought, boy, this is really the frontier. And over the course of the first 3 months, I started learning about the kind of things that I do. I ask a lot of questions, look into things, including finances and the technical progress and how one manages these very large, complex projects. And I immediately became very concerned that, in fact, James Webb would never launch. At the rate of progress we were making, because of the way that it was budgeted, the way that the technical progress was going. And I sort of recall reading about similar experiences with the Hubble Space Telescope, so I went to my bookshelf and I pulled off a book called The Space Telescope by Robert Smith. And I went through it page by page and started highlighting critical paragraphs here and there. And then came in to see Matt in March of 2010. And I said, I want to read you some things from this book called The Space Telescope, keeping in mind that this was written before the Space Telescope that Hubble launched. Now, this, of course, the seminal book for Robert Smith. And Cambridge University Press. Do you have a copy handy? So anybody who wants to know this. And I read Matt selected passages, quite a few, and every time it would say Space Telescope, I would insert James Webb Space Telescope. And I said, we're in big trouble because this reads exactly like Hubble, and we should learn from that. And then I brought him a bunch of space superconducting, super collider stuff. And I said, this is what we have to avoid. And we did exactly that. We learned from it. We called Garth Illingworth. We put together an advocacy group and used the existing James Webb Space Telescope scientists that had already been put together to fend off what we had imagined might be an effort to kill the James Webb Space Telescope. And as you saw from our Clampin talk, we're now putting the telescope together. So we were successful in that. It was painful in particular for a number of folks that we recruited. But in the end, I think after James Webb was launched, after maybe 2 or 3 years of observations, nobody's going to remember the cost overrun, the technical problems, or the fact that we had to do all this work to keep going. Because it will be as transformational as Hubble. So we learned from it.
I'm glad that these stories are useful. Can I just add one thing? Because it seems one of the really key successes of Hubble is to make it possible that there be a James Webb. Because if Hubble had failed, it's harder, looking back, to have seen JWST merge. And so, you see what happened after the SSC got cancelled. The leadership in hydrogen physics shifted very much to Europe. And so there's a lot riding on the success of each of these really big missions, and there will be a lot riding on the success of JWST for the successor to JWST. And so success, I think, begets success, but failure begets failure. But these kinds of enormous scales.
But no pressure.
I'm going to take the last question. I'm going to ask, how did we get to be so risk averse in making these decisions? I mean, why should it matter if we build something and it doesn't work? Isn't that spur us on to make an even greater effort to succeed in the goal that we were pursuing?
Well, first of all, if you look at how audacious the James Webb Space Telescope is, I would hardly say that we're being risk averse at all.
I don't mean science, I mean
That's because members of the House of Representatives have to be re-elected every 2 years, so there's no tolerance for failure. Well, I better avoid that. And of course, senators, 6 years, the president's 4 years. It's a brutal environment.
I think sometimes also people don't realize the value of basic exploratory research and science that may not have an immediate apparent return, and yet it's that basic exploratory science that often sets the foundation for phenomenal progress later on down the line that you couldn't have predicted ahead of time. So you have to take some risks to do some basic exploratory science in order to build a framework for a future of abundant return. And a lot of times in sort of pragmatic atmospheres, we get short-sighted of that and are become risk-averse. But I think that carried to an extreme is harmful.
Do everybody in the audience who works for a venture capital firm? Okay. I was out in Silicon Valley recently talking to folks in the venture capital business, and we were talking to them about the kind of things that we invest in. There are hundreds of millions, if not billions of dollars, and that we have a very low tolerance for failure because of the huge investment. I sort of casually said, what if you were investing a few $100 million in a business? And how would you feel about putting together your team and investing and having it fail? That happens all the time. I don't know about hundreds of millions, but in aggregate, it is hundreds of millions, in fact, billions of dollars, and many of these businesses do fail. But the ones that succeed spectacularly. And so I think, in the business community, there is a sense of taking risks for big gains. I think in the political landscape, where everything is up, visible, and on a 24-hour news cycle, it's very hard for people to take taxpayer funds and fail. It's a much more difficult thing. And we may be going back to an era, and certainly true with large ground-based telescopes, where they're privately funded for just that reason. Space is a little bit harder.
I mean, I think it's this thing that Robert just said about scale. There is no doubt about it. There is real big scale changes in the projects we're having to undertake. And I think that's just that enormity of assembling those resources, both scientific, technical, but political, and social. It produces this very prominent program. And so a lot of people have to agree to take a risk. And that's the problem. It's fine if there's 5 of you in a room and say, who's going to take this risk? When you've got 1,000 people, the central limit theory, if you like, it's going to be very hard to get that 1,000 people to say, this is all or nothing. And the nothing is fairly bad too. So that's part of the problem. You're trying to assemble this very large coalition to do something where the outcome is uncertain. And the return to the individuals actually working on this, the point that Robert has made before. Very few people who start these big programs in the end really get to use them. The graduate students use them, and their postdocs use them in the next generation. So that's again a decision that people have to take. And you don't realize that until you start. That's the other problem. Think this is a good idea.
Of course, Hubble proves it's worth it.
Correct.
Before you go, you have a small gift.
Thank you very much.
Highlighted.
Great.
Yeah.
Thank you
So
very
we
much.
thank our speakers for our
Thank you all. Yes. Thank you.
Before we adjourn to the social hour, we have a few remarks that will bore you to death after this, but please. The PSW depends on enthusiastic participation in membership. Please join if you're not a member. And if you are a member, get involved in helping us carry out some of our activities. A nonprofit, educational organization, tax exempt under Section 5123, internal revenue code. Our next lecture will be this coming Friday. At 8 o'clock, and the speaker will be David Newman, who is about to become the Deputy Administrator of NASA, I hope, and she designs spacesuits. Would follow on to this talk. And then following that, we have Pam Silver giving the 84th Presbyterian lecture on synthetic genetics. And that will be on 8 May 2015 at 8 p.m. And forgive me for the error in the dues notice and begging letter for contributions that was sent out. But it is 8 May. Finally, the fall schedule is filling in. and we'll be posting it soon. To keep up to date on PSW programs, go to the PSW website at www.pswscience.org. So we do have a social hour, and it will end about 10 of. I don't know if anybody's going to go across the street after that, but sometimes we do go to the Fairfax Lounge, and we'll gather in the back, and if you go over there, you're welcome to join us. And with that, please use the side entrances to exit, and I'll accept a motion to adjourn 2,346 meeting to the social hour. Second? All in favor? All opposed? Meeting is adjourned.